Well, welcome everybody to, I don't even remember which edition of CARS workshop this is, Context-Aware Recommender Systems workshop. I guess I don't have to tell this audience why context is important in the context of recommendations and also more generally. There's been lots of work on context-aware recommendation in the past more than 10 years, I would say. In fact, I believe the first CARS workshop was 2010, if I'm not mistaken. So very early in the history of RecSys conference, CARS began, and there's been lots of good work done since then. And of course, the work on context-aware recommendation even predates that by several years. So over the years, there's been work on various notions of context, including, explicit context, implicit or latent context-aware recommender systems, and so on. And this work continues, and we will see some of that work today in this workshop. Let me just briefly introduce all of the organizers. So I'm going to share just the website for the workshop. One second in here. Apologize for the delay for a second. All right. Are you going to see that? All right. So
yes, I can.
Okay. Before talking about the program, actually, here are organizers. You can see most of us online right now. Actually, all of us. So get us. Konstantin, myself, Francesco, Alex, and Moshe, and special thanks to Moshe and Konstantin for doing a lot of the organizing and background work on this workshop for the past several years. So we are happy to continue working on this workshop. We have a good program today. So the program contains, we have two keynote speakers. I'll introduce Lucas in just a couple of minutes as our industry keynotes, and we'll have another good keynote talk later in the afternoon. So the keynotes sort of bookend our program, the rest of our program. You can find the program at carsworkshop.com/program if you like to take a look and look at some of the details. But after the opening, we're going to have Lucas's talk, then take a short break. Then we'll have a couple of the paper presentations, followed by another break, short break, and two more presentations, so a total of 4 papers. And then after the last break, we will have the last talk by Anand Bay, who's also done work on idea of context for quite a long time in computing in general, not just in recommender systems. Okay. Anybody else, any of the other organizers like to add something before we get started with the keynote address?
I just want to point out that in addition to whatever Bamshad said, the presentations and the papers are online in our website. You can find it in the program and also in the accepted paper section.
Thank you. And of course, the session is being recorded, so it'll be available, I assume, at some point later for people who want to watch it. Okay, so it's my pleasure now to introduce our industry keynotes, Lucas Meister from Spotify. Lucas is a research scientist at Spotify, has been working on improving users' long-term engagement and satisfaction. He's done a lot of work on probabilistic models for machine learning, developing affective models or computationally efficient inference algorithms. He got his PhD at EPFL, and his work was supported by Google Fellowship in Machine Learning. So we are all looking forward to hearing from Lucas. Lucas, are you ready to begin?
Yes, let me...
I will stop sharing. And by the way, before you start, if people have questions, please post it on the chat. You can also, of course, ask yourself during the Q&A session in person if you prefer it that way, or do both. So, thank you.
Thank you. So yes, hello everyone. It's really a pleasure to be giving this this keynote today. My name is Lucas. I'm working with Spotify. I'm based in London. And today I'll tell you a little bit about some work we've done on different aspects of context-aware recommendations. And before I start, I'd like to thank the organizers for inviting me, especially Moshe and Konstantin, who have been coordinating everything. So thank you very much. All right, so I'm part of a team of about 30 researchers who are embedded within this broader organization at Spotify called Personalization. And the mission of that organization is to match fans and creators in a personal and relevant way. And so we own a number of features and surfaces. Among others, there's the homepage of Spotify. So when you open the app, there's basically a screen that shows you a number of little cards that are personalized and contextualized. We also have a number of playlists that are personalized. So the goal there is to rank tracks based on your preferences and based on a number of other signals among a pool of candidates. And then also the search engine. So those are kind of some of the products that personalization is working on. And if I try to think of, some of the challenges that are perhaps, a little bit not straightforward if you think about recommender systems. So some of the things we spend a lot of time thinking about that are perhaps non-trivial. One is that Spotify increasingly is going beyond music and is also trying to become a service where you can listen to any type of audio. And so we're investing a lot in podcasts, for example. So we have to deal with these different types of content. Also, if you look at the mission statement, there's kind of an emphasis on both sides, right? There's the users, and we want to be as relevant as possible for the users, but then we also want to make sure creators get the exposure they deserve. And so that's, I think, an area where there's a number of very interesting challenges, really thinking about the two sides of that marketplace. And finally, and I'll get back to this at some point in the talk as well, there's kind of increasingly a shift from really short-term notions of success, like, trying to measure how much users are complying with the recommendations we give them, towards kind of a more long-term view of user satisfaction. And so that kind of opens the door to a whole new set of research problems, and how can you think about optimizing for the long term. So just for some backgrounds, Spotify, like a few numbers, there's 165 million subscribers. So those are users that pay a monthly subscription and that get access to unlimited on-demand music. And then there's altogether 365 million monthly active users. So the rest of the users have access to the free tier, which doesn't give you kind of on-demand access. You can kind of choose, a radio station, or let's say a kind of music you're interested in, and there are ads, but in exchange you don't have to pay anything. And as you can see also, especially in recent years, we've really expanded in many markets, which also comes with some really interesting challenges in terms of making things relevant across many different markets and cultures. So one of the reasons I also show this is because scalability is often a challenge, and actually, even in research, we often try to have engineering considerations in mind, because those are really very important in getting to a successful application of research projects. Okay, so with this, I decided to structure today's presentation in two parts. So the first part will be about perhaps a more traditional concept of context-aware personalization, where the goal is really to improve somehow immediate relevance by taking advantage of contextual information. And then in a second part, I want to somehow talk a little bit about context-aware personalization in the setting of, trying to go beyond immediate clicks and things like that, and try to think more about recommendations as a sequence of interactions with the user, where you don't want to necessarily, think about what you're doing exactly at a given moment, like one shot, but more as a sequence of interactions with the user. And I think in that case, context can also play a big role in terms of identifying perhaps opportunities to improve long-term satisfaction. So I'll start with really this perhaps more traditional notion of context awareness, and we're going to look at two projects that we've been working on at Spotify. The first one is really kind of a classical problem where we have explicit context that we observe and want to use it to perhaps anticipate better what a user is going to do during a session. And then I'll talk about a second project where context plays a very important role, but it's not directly observable. It's latent, and by modeling it still, in a principled way, we can drastically improve downstream performance in terms of the task we're actually interested in. So first project, the question we're trying to ask here is, can we use context as a way to better predict the music a user will stream during a session? So the setting is, we have Spotify's homepage, and imagine the user just opens the app, and we want to anticipate as well as possible what they're going to stream during that session. So inputs are, the usual stuff like static preferences, what we know about the user's preferences, maybe information about recent sessions. And then on top of this, we add two pieces of contextual information: the device that they're using, whether it's their phone or the desktop app or the web app, and the time of the day, whether it's morning, afternoon, or evening. And then we try to predict basically the music they're streaming during the session. So this is a work that was presented at RecSys last year, led by an intern that worked at Spotify in summer of 2019, that I'm going to present here. Okay, so first, some exploratory data analysis. So we have these two contexts that we're interested in: the time of the day and the device. And so we wanted to look a little bit whether there was, an opportunity to use this as a way to improve our predictions of what users are going to do at the beginning of a session. We have this data set with where we look at users' sessions over a 2-month period, I think it was, for a sample of 200,000 subscribers to Spotify. And we can just plot the histogram of different contexts that we encounter in this data. And we see that for time, there's reasonable contexts are represented, across the different options that are there. A little bit less heterogeneity for device. But okay, so that's just, kind of at a high level, like marginal statistics about how contexts are represented in the sessions data set. But then we also decided to look at for a given user, maybe a given user is always using Spotify in the afternoon. That's just maybe their habit. So maybe if you think about a given user, it doesn't really make sense to look at context. But actually what we observed is that most users encounter multiple contexts within the window of data that we had, which was 2 months. And that was extremely the case for time, and maybe a little bit less for device, but still, even for device, given the imbalance that we see above, it's quite striking to see that most users encounter multiple contexts. So that's kind of a motivation for looking into these variables. Now, the other thing that we need, of course, is that differences in context somehow predict or correlate with differences in content, right? In kind of the content of the session that happens. And so, yeah, I'm not going to go into the details of the plots below, but basically we were able to convince ourselves that even controlling for differences across users, because of course some users are going to listen to some type of music and prefer perhaps some times of the day or some devices, but even controlling for all of these things, we can observe a very kind of reasonably strong correlation between the context and the content of the session. So that kind of indicates that there might really be an opportunity for predictive models to leverage that context to improve predictions of what a user is going to stream in a session. So before I jump into a description of the model and the results, let me do a quick detour and tell you a little bit of how we think about music similarity at Spotify. And so this is really one of the core, let's say, abstractions that we use throughout many of our personalization features. So we have these track embedding vectors that encode some similarity between, some notion of similarity between tracks. And it's learned using some variant of collaborative filtering. So the way we learn these vectors is that we take user-created playlists, and the signal that we use to train these vectors is that we try to push the similarity towards 1 when 2 tracks are likely to co-occur within a playlist, and we try to somehow push the similarity down when tracks are unlikely to co-occur. So we typically sample negatives to somehow, yeah, get the 2 types of signals in the training data. And so the takeaway from this is that from these user playlists, we can learn this 40-dimensional vector space where every track is a point in that space, and distance in that space essentially captures musical similarity. So, okay, so now let me describe the predictive model that we came up with. So again, to recap, the goal is at the beginning of the session, we want to predict tracks that will be played during the session. So we assume we have access to all the information that would normally be available to us at the beginning of the session, which is, static preferences, recent sessions, and then time of day and device used for that session. And perhaps what's interesting in this model, and what I want to draw your attention to here, is that this model outputs actually a point in that track embedding space. So there could be many different ways of modeling that problem. I guess a common one would be to see it as some kind of giant multi-class classification problem and output somehow a probability vector over tracks ordered by how likely they are to occur within the session. What we do here actually is that we reuse this existing track embedding space, and our model outputs a point in that space with the assumption that tracks within the session are going to somehow be in that corner of the space. So the way we train the model is by maximizing the cosine similarity or minimizing the cosine distance from the predicted point in that space to the tracks played during the session. So again, I'm not going to go into the specifics of the model. It's a recurrent model that uses a number of clever insights to try to combine, these various inputs in the best possible way. But really, maybe the interesting bit here, I think, is really how we chose to model the output and represent somehow the prediction as a point in that track embedding space. And we measured the performance of this model on two tasks, two downstream tasks. One is try to discriminate the next session from further sessions in the future. And another is to try to predict which tracks are going to be in that session. So it's basically two types of ranking tasks. And we consider a number of baselines, some really simple straw men that look at recent sessions or things like that, as well as more complex and sophisticated state-of-the-art sequential models. And it would take a lot of time to go into the results and details, but I just wanted to I guess highlight two things. One is that we do observe improvements in predictive accuracy by using context and by using the specific architecture of the model we developed. But what struck us particularly, and I think what made us quite happy as well, is that it seems that the improvement, if you break it down by session context, is particularly large in contexts that represent a minority of the data. So it seems that when there is something special, that's when our context-aware model is particularly, gives a kind of has a particular edge over, let's say, more traditional approaches. For this project, really the takeaways is one, context really seems to matter. So without even looking at the specific model we used, I hope I convinced you that there was evidence that contextual information, in this case time of day and device, correlates with the music that people stream in a session. And then, of course, that's kind of an opportunity for particular recommender systems to try to leverage this and improve relevance of the output that they produce. And the second aspect, and this is maybe one interesting takeaway from an industry perspective, is I guess one of the challenges of context-aware recommender systems is that to some extent, they really need to make predictions in real time, because the output depends on the timely signal that is perhaps available only at the moment where you want to display results. And so that raises a certain number of engineering challenges. And there are two ways in which we tried to make it as simple and easy as possible here. One is to really rely on this existing shared representation, which we took as kind of a common language across personalization systems. So that makes it really easy to interface with other services and features. And the other thing is, the more you can pre-compute, the better. And the more you can avoid making costly model inferences as serving time, the better. And so in this case, because we have these discrete contexts, we could potentially pre-compute a small number of predictions for every user based on what we think the contexts they will encounter will be, and pre-compute all this, and at serving time just use a lookup table or something like that to really make it as efficient and simple as possible. So that was for an example where context is observed and we really, take it as an explicit input into the model. But there are cases where context is very important, but is not necessarily observed. And this is the case in this work that was authored by some of my colleagues and presented at KDD earlier this summer. So the question they asked is, does modeling context help discriminate between music and podcast search queries? So the context here is, or the setting is search on Spotify. And a few words about our search engine, some characteristics. So its results are instantaneous. It's kind of a search as you type system where, as users add in characters, the ranking kind of changes and gets really displayed as they type. There's heterogeneity. So this is really the part that's going to interest us here. Users may be searching either for music or for podcasts. And obviously, this is going to have a huge impact on what results are relevant and which ones we want to surface. And then there's also challenges around multi-representation. So it's not only about matching the text of the query to, you know, some text describing the content. There's like much more complex representation of contexts and queries that we need to use. But I'm not going to talk about this much today. So really what I'm going to focus on here is this idea that there's a latent context, which is whether the user's intent is to find music or podcast. And this is like explicitly modeling this is going to help us a lot. Again, some exploratory data analysis to convince us that, you know, behavior is a bit different when you search for music or podcast. Users seem to put in more effort when they search for podcasts. So the average query is longer as measured by the number of characters, and they are more likely to refine it and delete characters and kind of, yeah, rewrite their query multiple times. Also, the way results are consumed once the search query is issued is different. So what struck me is that it seems that users, when they search for podcasts, they typically, they're more likely to save it for later than when they search for music. So either download it or add it to a collection. So with this in mind, so that really the key goal of this project was to you know, rank the results as well as possible, putting the most relevant results first for a given query. But knowing that there's this latent context that strongly influences the relevance, my colleagues decided to explicitly model search intent. So the way they did this is by setting up a multitask model with two losses. There's the traditional ranking loss on the left. And then there's also a binary loss on the query intent, which is basically a prediction, is the user searching for podcasts or music? And the way the label is determined there is just looking at the item that gets clicked in the end and looking up whether it was a podcast or music. And so what's interesting is that at the end of the day, all we care about is really the ranking, but explicitly adding this item identification loss helps the model rank results substantially. And so I just highlighted one of the metrics they capture in an ablation study where they look at the performance of the model with and without this query intent type identification. And with the full model, performance increases substantially. So takeaways here is really that beyond context that we can observe, there is also latent context that plays an important role, and explicitly modeling that latent context can help the task we really care about here, which is, in this case, ranking search results. So yeah, that's it for the first part, which was looking once again at this more short-term notion of relevance and using context for that. Now, there's really this increasing shift towards viewing recommendations through, you know, the lens of really a sequence of interactions with the user. And it's really kind of grappling with things like delayed consequences and intertemporal trade-offs, and with the goal of really improving long-term satisfaction. So not necessarily session level metrics like how long did the user stream, but really trying to think, is the user going to remain a subscriber perhaps 6 months from now or 1 year from now? That's one of the ideas we could have for expressing long-term satisfaction. And I guess the idea here is that I think that there's a lot of the literature and context-aware recommender systems that could, I think, play a role in kind of shaping this and improving these aspects as well. And so there's kind of a broad notion of context that we could consider as the state, like at what stage of a journey is the user, what's kind of the history of interactions the user did so far, and we can really use that state to perhaps not only improve relevance, but also maybe identify what are good moments to improve maybe long-term goals we have for kind of a long horizon in a sense. And so I'd say this is really a topic that we're investing in a lot and that we're spending a lot of time thinking about. I feel we're still relatively at the beginning of this, but I'm going to highlight one thread of research that goes a little bit in that direction around diversifying users' preferences. And so the research that kind of spawned this was more of an observational study of how users' consumption diversity relates to their long-term satisfaction. And this is a paper we presented last year at the World Wide Web conference. So the idea is that if you think back about the track embedding model that I talked about a couple of slides ago, we have this space of music in a sense. And we can represent every user by, the point cloud of the tracks they listen to, right? So the idea is that some users are like user A, and the tracks they listen to are somehow spread out in that space. They might listen to classical music as well as, I don't know, electronical dance music and jazz or something. And then there are users that are more like user B that might, stream just as much, but perhaps in a much narrower region of the space and listen just to, maybe a few related artists or kind of a very specific genre and just stick to that genre. And so to measure this, we devised this metric called the Generalist Specialist score, which builds on top of this track embedding space. So the idea is really very simple. You start from this track embedding space, you represent every user as a point cloud by taking every track they streamed in the past, say, the past month, perhaps weighted by number of times they streamed it. And you compute somehow the volume that this point cloud takes. And so you can make this formal, with some formulas, but really the idea is this, is like how voluminous is this point cloud that captures users' consumption. So a user that has a diverse listening and has tracks all over that space, we would say that this user is a generalist, and then a user that has a much more concentrated consumption around kind of a narrow region of the space would be called a specialist. So we can compute this metric for every user on Spotify. And with this score, we can then ask questions like, how does, where you are on this generalist specialist spectrum relate with long-term outcomes? So one thing we looked at is retention. So we took a sample of subscribers and we computed the GS score for these subscribers sometime in 2018, let's say July 2018. Then we look 1 year later, July 2019, are they still subscribers or not? And we just plot the correlation between their GS score in 2018 and whether they're still a subscriber or not in 2019. So in this plot, we normalize everything with respect to the average churn rate. So higher churn means kind of a worse outcome, means that people are leaving. Lower churn means people are staying. And the x-axis here is the GS score. So on the left is like more diverse users, on the right, less diverse users. And what we observe is that there's really kind of a strong correlation between GS score and churn rate, in a sense. And so at the extreme, between extreme generalists and extreme specialists, there's almost like a 25 percentage points difference in churn, which is obviously kind of a huge numbers in terms of business impact, if you think about it. So in this plot, we're showing this for different activity buckets, because obviously there's a concern that maybe activity is confounding our diversity metric as well. But it turns out that for various levels of activity, so overall engagement, there's really a strong difference between generalists and specialists. And perhaps what's even more striking is that this difference, actually diversity is a better predictor of churn than activity, which is something that really struck us and that we thought was remarkable. So we did a similar analysis with conversion. So those are users in the free service. And we look at whether 1 year afterwards they convert to premium or not. And the story is kind of similar. So the more generalist you are, the more likely you are to convert, within a year. And this holds again across activity buckets. And there's again a kind of a very strong difference between extreme generalists and extreme specialists. So controlling for activity, more diverse users are more likely to become subscribers. So takeaways really here is that high diversity is associated with really positive long-term outcomes as measured by conversion and retention. So of course, the million-dollar question is like, is this kind of a causal relationship? Is it true that if we were to somehow introduce users to new genres, they are more likely to convert or more likely to retain? Or is it just, all due to some higher love of music or something like that? And this is a question that we're really investigating and spending quite a bit of efforts, because it's an important one. But probably the question is like, there's part of it that's causal. So assume for a moment, and for the sake of this presentation, assume that, part of this link is causal. Like diversity does increase your long-term satisfaction. How would we go about diversifying users' consumption? One way would be to just, inject random tracks, but I think we can all agree that this is unlikely to work. So how do we do it in a meaningful and clever way? So this is the question I'm going to look at in one slide. But before I move on there, I just wanted to highlight that there's a paper at this year's RecSys by some people from Google that look at something very similar. So they also look at somehow long-term satisfaction, and so they look at it in the context of a reinforcement learning system. And they kind of think about diversity in terms of exploration and so on, but they have somehow insights that are really quite well aligned with our findings. And it seems that things like what they call serendipity, which is kind of our diversity, seem to be extremely important for long-term satisfaction of users. So, all right. So the next stage is really, okay, given this finding, how do we go about progressively introducing users to perhaps a new region of that music space? And the picture we had in mind here is, think of music space as like a collection of little islands. And perhaps a user is on one of these islands, say pop. And then the question is, can we somehow map out the best way to bring a user from pop to jazz? And so maybe there's kind of a series of gradual steps that we can take to bring the user progressively there. And so in this case, there's a notion of, where is the user along that journey, and can we somehow think ahead and somehow map out such a plan. So this is something we explore in a paper that we presented at this year's WWW. So the data we use in this case, in terms of describing music, we use a slightly different description. So we're no longer in that track embedding world, but instead we use a collection of microgenres. So those are a little over 4,000 labels that describe like very fine-grained musical genres. And then we have this data set of 100,000 subscribers, and we describe every user as a time series of vectors. So at each point in time, a user is described by a 4,000 dimensional vector, which describes how they allocate their streams across these 4,000 different microgenres. We have these time series for every user. And yeah, every step corresponds to 3 months, so a quarter. And we look at really 4 years of data. So it's very kind of at a very large temporal scale. And what we want to learn is whether there is some regularities in how users somehow shift from one genre to another. And we proposed this very simple model, which we call the preference transition model, which is essentially some kind of first order Markov chain model. So we try to predict what a user is going to stream in the next month by multiplying somehow a vector that describes their consumption on the previous month by a transition matrix. And so the parameters in our model are this transition matrix A that tells you how much listening to genre I somehow predicts that you will listen to genre J at the next time point, so the next 3 months. So the nice thing about this model is that it's pretty easy to train, and the parameters are highly interpretable. So we have this matrix and we can really understand what each entry in this matrix means. And we can reinterpret this matrix as the adjacency matrix of a directed graph. And with this, we can somehow construct this graph that, tells you how to reach, how to go from one genre to any other genre by taking somehow manageable small steps. And the idea is that we can use this really as a map to progressively bring users, say, from classical to modern blues in a progressive way. So yeah, takeaways here is that there's really consistent patterns that we can mine from longitudinal consumption traces, and by learning these patterns, we could potentially introduce users to new genres in a kind of a gradual and meaningful way. And so here, really the setting is that we think of context as a notion of state. Where's the user along that journey? And we're somehow planning recommendations over many interactions. And with this, it's time for me to conclude. So just to recap, in the first part of the presentation, I talked about this more maybe traditional notion of context for short-term relevance. And I hope I convinced you that there's evidence that both observed and latent context help predict user needs. And I also briefly mentioned engineering challenges and how to overcome them pragmatically. And then in the second part, I kind of shift gears a little bit and in the context of this increasing shift towards a sequential viewpoint and long-term goals, I think there is really an opportunity for ideas from context-aware recommender systems to improve somehow how we approach recommendations for the long term, by identifying opportunities to improving long-term satisfaction and planning decisions over multiple interactions. And I feel this part is really, it's scratching the surface, and I think there's a lot more to come there. So yeah, with that, I'd like to thank you for your attention, and I'm happy to take some questions.
All right, thank you very much, Lucas, for an interesting talk. If you have questions, you can raise your hand on Zoom, or you can type in the chat if you like. So I see already Francesco has raised his hand, so go ahead, Francesco.
Okay, thank you. Thank you, Lucas. Very, very interesting talk. Thank you for being very, very clear. But I have a lot of questions, but I will just keep it short and just a few of them. First of all is on the first paper where you talk about, let's say, this context, which is the time and the device. But then you talk about this embedding on this four-dimensional space, which is related to the, let's say, co-occurrence. So in our understanding, this type of embeddings are representing the context, which is implicit in this, let's say, co-occurrence relationships. So I would also imagine that this is representing this hidden context, which is not clear. They clearly defined like let's say the time and the device. But have you tried to understand why the meaning of certain dimension? Because I imagine it could be related to this implicit context. This is the first question that I have.
Yeah, I see. So you're okay. That's a very interesting question. Yeah, we didn't really look into this, like basically trying to interpret, perhaps instead of fixing context up front as being time of day and device, looking at whether they're like the dimensions of these this 40-dimensional embedding that might explain some latent things. That's so the way we viewed this this embedding was more kind of as a pragmatic way to express something in terms of music content, not as a way to really mine context. But yeah, I think that's definitely interesting.
If I can add the second question, very, very quick question. It's about this the other paper that you presented about this retention and the diversity, the experts and now the specialists and the generalist. I'm not that sure that this is related with diversity. Now, I don't know that just a guess. Obviously, let's say specialists are just listening to one type of music. Don't you think that could also be related to the fact that the type of usage of the platform for this type of specialists is very, very limited, so that competitors can capture this type of users, but they are not exploiting really the platform like the generalists, which are maybe using the platform in more and more sophisticated way, so then they stay in the platform for that reason. So it's a matter more related with the type of the usage of the platform, the functionality of the platform that obviously is correlated with the diversity, but I don't know whether it's really the diversity that matters. I don't know whether it's clear, my question.
Yes, no, it's very clear. And I think, yeah, you're spot on. I think there's really a lot, and I think this is really the interesting bit about this work, is that there's kind of a huge correlation, and it's really striking, I think. But then it really raises the question, like, how do you explain this? And I guess to some extent you are right. I think it's true. Like probably people who have this more who are more diverse, it's maybe a sign just that they find more value across multiple parts of the platform. I really, I had to go pretty fast, and we're looking into some more interesting things in the paper. In particular, one thing that maybe might be, interesting, I think, in this discussion is that one thing that we observed is that recommendations on Spotify seem to serve specialists better. So when you have this very narrow preferences, then I don't know, we can understand them more easily, and somehow, our recommendations are more spot on, and somehow generalists, we have kind of a harder time serving them well. And so maybe one of the questions that comes out of this is like, is there something we can do? Because it seems that the generalists are those that really, have a high value, and that we might need to somehow cater to better in a way. So there's a whole aspect of the interplay between, this metric and what it says about the user and algorithmic recommendations that I didn't go into too much, but that
Thank you.
Kind of is very interesting to study in itself as well.
Thank you.
So there is also other questions. In fact, this was one of my own questions, kind of piggybacking on Francesco's, about the causality versus correlation of the what you call the GS score and and the willingness to explore and so on. And one of the things, and Francesco touched on this, is that maybe the type of user is different, right? So perhaps they need different metric for satisfaction. So if you're trying to measure the, a user maybe that's very focused on one type of music, perhaps has a different goal when they're listening to your platform than a user that uses it as kind of a way to explore, right? So different types of users, but the satisfaction for those two users perhaps should be measured differently, not necessarily in terms of how long they are engaged with the platform. In some ways, that focused user may actually satisfy their needs much more quickly, for example, than somebody who just is interested in long-term exploration. So interesting question. I don't know if you wanted to add any more to that.
Yes, absolutely. Yeah. So I hope I was careful to say that, this is, we found associations, right? But for sure, the question of, what is exactly the causal effect here is still open. I mean, I cannot share too much, but one thing I can say is that I think we're pretty convinced that at least part of it seems to be causal. Like maybe not the whole effect is, maybe there's some confounding going on. And indeed, retention for generalists might not mean the same thing as for specialists, and so might be explained in other ways as well. But it seems to be that if we can bring users to start, I guess more broadly than just musical genres or different parts of the musical space, I guess it goes back to bringing users to find value in not just maybe one narrow part of the app, but kind of other things as well. It's somehow a good way to make them, happy over many months.
Thanks. Alex.
Yes, somehow Francesco asked all the right questions. So Bamshad has the question related to the second question, and I have the question related to the first question which Francesco asked. So great minds think alike, Francesco. My question is, so you had this latent representation of music, this 40-dimensional vector, and you have explicit representation of context, device, and time. And then in your diagram, you feed them into the LSTM model. And so clearly somehow you combine the explicit and latent representation. And you went a little, correct. You went a little bit quickly over it. My question is, can you talk a bit more about this process of combining explicit context with latent representation, basically latent versus explicit, and combining the two?
Well, so
because there are lots of issues there, right?
Mm-hmm. So in a way, in our model, everything is explicit. So you're correct that I guess one way we could train this model is to, have this explicit context and then jointly learn the representation of tracks and the, I guess, and the kind of the task we're interested in, which is predicting what's going to be in a session. But in this, in our case, we actually use this existing 40-dimensional embedding, which indeed is, learned through another model and with some kind of implicit signal. But in our model, it's in a way, everything is explicit, what gets into it. These embeddings don't get trained further. So the way they get combined is basically, you have a context. In our case, are these discrete bits of information, right? So which time of the day it is. So it's just kind of encoded as a one hot vector and concatenated to say, the embedding of the previous session. And then this is all, fed into a neural network that then somehow learns to pick up the patterns that somehow help predict the output.
Right.
But this is maybe something I want to emphasize, and I think this is kind of this is something I kind of learned to appreciate also at Spotify and in industry. We found it important to somehow stick to this existing embedding space that is learned independently and maybe with a different data set, and then use this kind of as a given and as a space to operate in for our contextual model.
Okay, we are almost out of time, I think, but there's one question on the chat. Maybe you can quickly address, or a couple of them. Did you try other contextual features other than the time and device in terms of the explicit features when you were using this model?
Yeah. So, okay, we didn't try a whole lot, but one that I can briefly talk about and that I think is interesting is we thought, what if in addition to knowing the time of the day and the device, we know which feature of the app you're going to use. So is it going to be, a playlist? Is it going to be still kind of at a high level? So of course we don't know which playlist or anything like that, but kind of which feature of the app, kind of keeping in mind, like with the idea that maybe, it's not at the moment the user opens the app, but maybe when they click on the feature that we can make a prediction. And this kind of really substantially increases the accuracy of the prediction. So there's even more signal in if we know where in the app the user is going to go. So this is one thing we looked into.
Okay, thank you very much, Lucas. Excellent talk.
Thank you.
So good work. And we do have, there might be another question or two on the chat. If you feel free to respond to it on the chat, if you like. We have a break until for 10 minutes, I guess. Then we're going to start with the next session. So we'll take a short break here.
Thank you, Bamshad. If you're presenting in the next session, please send me a message. I will make you a co-host.
Hello, Konstantin. Can you hear me?
Yes, the sound is not good. I hear lots of echo.
Yeah, okay, so let me, I wanted to try the different mics I have. So let's try this other one. How about this one? Does it sound better now?
No, it's the same.
Okay. And how about this one?
Nothing changes.
Okay, yeah, so it's...
Make sure that you're changing the mic in the settings of Zoom, not in your preferences of your computer.
Yeah, exactly, yeah, that's where... but so now... let me try to take off my... I put my video, just to make sure you see me correctly. Can you see me?
We can see you. Yes.
Okay, got it. So I'm going to take off my AirPods just to make sure they get disconnected. And then I'll try with this other mic. Does it sound any better now?
No, everything is the same. Nothing changes.
Okay, so now I cannot hear you. And yes, let's see. Try this one. Okay, how about now?
I hear the same.
So, yes, so it's. I'm sorry for that. Because it's. I've been changing between the three, so maybe see if I also need to change system preference. But that's why I wanted to try before. Input. And how about now?
The same. I think we just need to live with that.
Yeah, exactly. Yeah, it's or maybe it's just the tone of my voice at 7 in the morning. Cool. Do you mind if we also try a second to share the screen? And also, like technically, I'm going to share the screen in the first half, and my colleague Kat is going to share the screen in the second half of the presentation. It might be a little bit of a break between the two, right? But again, like if when she talks and I need to go ahead with the slides, it's going to be more disruptive overall. So I'm going to try sharing the screen.
So who is going to share the screen?
Me, Emanuele, in the beginning, and then you're going to see Kat, which is going to take over at half. So I don't know if Kat is already here, a participant, but I'm sure we can. Do you mind if I try sharing my screen just to make sure?
Yes, Moshe, can you please stop sharing the screen? Yes. So there is a message in the chat saying that there should be an echo cancellation option. You should go to settings, audio.
Yeah, the problem is that I'm calling from the web app, so I don't think there is I'll try in the settings.
Yeah, but there still should be some preferences.
Yeah. So I've got general, when I can put my background, and there is an about. So unfortunately, there's not an option that I've got right now. And then, okay, so let me try to share my screen just to make sure.
Okay.
I think, okay. Small, but I want to see. Okay, it's not presentation mode. So choose what to share. I want the window. Then, so it's can you see my screen now or not?
No.
Okay, that's good. Just a little bit of time. Okay, now is it going? But now I think I'm sharing all the screen, right?
So we do not see your screen.
Okay, got it. Try again. So the window, Microsoft PowerPoint. Can you see it? You cannot see anything right now, right?
Wait a second.
Okay.
No. I do not see anything.
Okay, I need to allow screen recording as in system settings in your device system setting. I need to do. Screen recording.
If you have any problems with sharing, I can open your presentation and share my
Yeah.
screen.
Yeah, I think that's an idea. So let me see if I can get to. Thank you so much for offering that. I'll try to see if I can activate it from here screen.
Okay, let me check. Maria, the second presenter. Maria, are you here?
Yes, I'm here.
Okay, glad to hear you. So yeah, nice to see you. So
Nice
I made
to see you too.
made you co-host. Your sound is great. You don't have any echo. You should be able to share your screen as well.
Do I try to share the screen?
You can
My
try.
screen?
Yeah.
Okay.
Yeah, perfect. We can see your screen.
Okay.
Oh, great. Who is sharing screen? Kat is sharing screen.
Sorry, does that work? Can you see the screen?
Yes, we see a
Okay.
screen. So you will do that, yeah?
I can do that then if that works for you, Emanuele.
Perfect.
I think it would be great, Kat.
Or
Thanks.
you can try again.
Yeah, and let's see if my video works. You can see me, right?
Yes, we can see.
Yeah, thank you so much, Kat. So it's. I'll tell you when to go to the next slide. Sorry.
Okay, so
yeah.
So wait a second. So let's everyone please come back. We are continuing our workshop. Now we are starting the presentation of our papers. We will do 2 presentations, then we'll do a short break, and then we'll do another 2 presentations of papers. So our first presentation is the paper called a Scalable Model for Online Contextual Music Recommendations. And we have 2 presenters, Emmanuel Coviello and Catherine Ellis. Please present. Sorry, you will have 15 minutes for your presentation, 5 minutes for your questions and answers. Please track your time. Otherwise, I will interrupt you after 15 minutes. Thank you.
Thank you, Konstantin. Hello, this is Emanuele, and I'm presenting work with we've done in also music with my colleague Kat and Fabian. And so this is a scalable model for online contextual music recommendation. In our bid, we experiment with the recommended models that support several personalization experiences across Amazon Music, ranging from Alexa on voice, personalized search, and the personalization of the homepage of the app. And our goal is to build personalized recommenders that are based on users' taste, they're relevant for the context, and also presented in an intuitive way. And so this talk specifically focuses on an application on the Amazon page, which is organized as depicted in this sketch. So we have a list of widgets for recommender, each one has a title and has a specific template, and displays a collection of entities such as like albums, tracks, playlists, and so on, but is presented as a scrollable carousel. So the idea here is that people generally relate to their music taste in terms of a richer list of like style, aesthetics, even moods, no? And different customers may respond to language of music like differently, perhaps differently in different contexts or depending on the activity that they are doing. And so that's why we are interested in building and supporting this variety of faceted recommendations. By faceted, we mean like a attribute-based recommendation. So some of them may be based on like an artist you're familiar with, like a genre, micro-genre, or like description that might have to do with like a time of the day or like an activity like focusing. You can go to the next slide, Kat's thing. And so this is just an example. So we have this variety of templates. Each of them is, for example, defined as like new releases in genre, where genre is the facet or like couple of dimensions that we're building building this experience across. And again, we might have like single facet recommender or multi-facets like mood genre or era genre. And so in the paper, we have presented an architecture to enable launching this type of faceted recommenders. And so one important design aspect for us was to like split the seed selection and content selection portion of these recommenders. So in the seed selection, we first allocate the theme of a recommender, and then in the content selection condition on the theme, we select content that's relevant for the customer and context. No, and really here, this modularity for us, it was important so that we can improve and troubleshoot the two different components separately. And also, like, we gain like interpretability of a system. So I'll begin by covering the selection portion. No? So the idea here we have like template faceted recommender, and so the idea is that we might have a recommender like more like artist, and the goal is simple. We need to choose the best seed, in this case the best artist, given the customer's preferences and contextual information. And for example, here we may have new release in genre and more like artists, and we might select the Jazz and Rihanna, for example, like the best seed for the customer in question. Then, so the way we accomplish this is using like a bandit problem. The idea is that we have an agent that interacts with the user and of the environment, and the agent has access to like actions. In our case, might be a genre, for example, that we can use in a genre recommender, and then the agent has access to like context features that describe the user context and taste, right? And then makes a recommendation by selecting which recommender, which genre to show a recommender about to the user. And then like the user interacts or not with the recommender, which signifies like getting some feedback for the agent. And here the goal of the agent is to maximize this positive interaction or feedback with the system. The reason we chose contextual bandit here is because we have several good properties for us. We can adapt to changing behavior. For example, the catalog change over time. Maybe some more genre become relevant. They are programmed more often. Maybe the population of consumers in the app like shift over time. Maybe you can reach like a different demographic and so on. Other things that like contextual bandit are like simple. They are efficient in handling data because they only use a single data point once for training, and then they have a built-in way of balancing exploration and exploitation. So I just skip very quickly on the next slide, but again, the idea here is that in f of x of a, like we model both action and context features, including the interaction. This might be a simple function, concatenation, including interaction terms, or it could be like a more complex neural network. So these are some experimental results that we did on the seed selection portion of our genre recommender. The control was we simply get a randomized genre from your top genre, from your history. In the treatment, instead, we use contextual multi-arm bandit to select the genre. And so we used like a variety of action and context features to support for this experiment. In particular, the context features range from like customer habits, for example, in terms of genre consumption in different windows of time in the past, but there's also like a customer preference to familiar content versus like recent content and so on, as well as like a feature that might encode what the customer has done recently in terms of following new artists and how that maps to genre. So just go very quickly here. And so the results were overall like they gave us like a substantial lift in engaging in these for customer to engage with this type of recommenders. In particular, we use this like metrics in this paper, the fraction of on-page customer that interact through a successful playback at least once through a window of time, and we got a significant lift there. And as well as the average number of like a successful playback per customer that are attributed to the version of to this recommender. No? And we saw that in general, on both of these metrics, using the contextual seed selection model, a substantial increased engagement. And I'll give the word to Kat and I'll skip the next slide for the sake of time.
All right. Thanks, Emanuele. So Emanuele talked about seed selection, and now I'm going to talk about content selection. So that means given a specific recommender template, user context information, and some pre-specified seed value selected using the multi-arm bandit that Emanuele just described, the goal here is to select the best content to serve in the recommender. So same as with seed selection, here we're using a multi-arm bandit to select content. The key difference, though, is that rather than the agent returning just a single action or selecting a single action, the agent selects a ranked list of actions to present to the user. And then in return, the user gives feedback on each one of those actions in the ranked list. So now that we're presenting ranked lists of items to users rather than single items at a time, we need to think about presentation bias. So it's a well-known problem in recommender systems. Eye tracking studies have shown that users are more likely to look at the top left side of the page. So if we compare the performance of actions from the top of the list to actions at the bottom of the list without accounting for this presentation bias, then we could be disproportionately advantaging the items that were ranked at the top. So one useful tool for dealing with position bias is the position bias model. And it makes this key simplifying assumption, which is that we can decompose decompose into relevance of the action to the customer context and some position bias term. So here C is the observed reward for the action in context X when it was shown in position K. And the position bias model assumes that there's some true underlying relevance R for that action in that context, but it's masked by this binary random variable O, which denotes whether or not that true relevance was observed. And the key simplifier is that we're assuming that the probability of observing the relevance depends only on the position K that it was put. It doesn't just depend on the action itself, nor on the context. And of course, this is a simplification. It's possible, and actually we've seen that the position bias can change depending on the context. For example, like a device with a smaller screen will show fewer items than a device with a larger screen, so it's less likely that a user would see items further down the list in a smaller screen. A simple way we can deal with this is just to partition models into contexts that share similar position bias models, but it's an interesting area for further research. So extending the concept of position bias to the linear bandit in the ranking case. So even online, we don't observe the true relevance for every action that the bandit selects, like we would in a standard top one case, because those rewards might be masked by the observation random variable. So the expected payoff of an action also depends on the position that it was ranked. And practically, that means that when we update the bandit, given the observed feedback we see, we compare the observed feedback to a scaled predicted reward where it's scaled by the position bias. So this is a specific experiment that we ran on content selection. So the same genre-based recommender. So this is given that we've already selected the genre seed for a recommender, how can we select the content? And so for this experiment, we used an ensemble of 2 candidate generators. So one was based on popular content within the genre, and the other was based on personalized content within the genre. That's using a user-to-item collaborative filtering model. And then we used the ranking multi-arm bandit to blend those candidates and produce a final ranked list of content to recommend. So these are the specific treatments that we looked at. So all the treatments are using 2 candidate generators, but we tested different ways of ensembling and blending those candidates to produce the final ranking. So one was just using that same user item collaborative filtering model. Another was randomized, and then finally we used the ranking multi-arm bandit that I just described. So the features that we used for the ranking bandit are similar to the ones that Emanuele described for seed selection. So there's a variety of context features like device type and temporal information, action features describing the actual entities that are available to be recommended. So something like the popularity, the release date, entity type. And then we also have a variety of interaction features. So something like the interaction between the release date of an entity and the user's preference for newly released content. And looking at the results of this experiment, what's important to notice is that ensembling in the more personalized content did improve engagement, but only when we used the contextual features with the contextual multi-arm bandit to properly combine that with the popularity-based content. So you can see the T3 here is the multi-arm bandit. When we saw a 20% average relative lift in the fraction of users with at least one successful playback on the recommender. Yeah, so to summarize our contributions, we developed a scalable architecture for serving faceted music recommendations. We experimented with both seed selection and content selection. These experiments were specific to a genre recommender, but the architecture is generic and scalable such that it can be applied to many other recommender types. We're using a contextual multi-arm bandit for seed selection. And for content selection, we're using a ranking multi-arm bandit and ensembling multiple content generation strategies. So thank you for listening. Any questions?
Thank you for being right on time. Do you have any questions? Yeah, Francesco raised a hand.
Yeah, my question is about the usage of bandit and the comparison between the content selection and let's say gen selection. I would expect that it's much easier to use this type of approaches for gender selection rather than content selection because of the diversity of the content. Can you elaborate a bit more on that, whether you find that this approach is more useful in one of the two situations?
Can you explain a little bit why you think diversity would make it more difficult?
Because you have more arms, and so it's you have less feedback for each arm when you have the content that you have to personalize with the multi-arm bandit, unless you cluster the content in some way. That's my guess, but I don't know exactly how you use this multi-arm bandit. So unless you do an embedding, unless you do something in order to transform the content into a lower dimensional space.
Yeah, well, I think two things are that one, we are using features of the entities or the available actions rather than like one-hot encodings of each action. And we have item embeddings that are features that we use as well. So that's part of it. Also, if you saw the results, the seed selection model experiment did show a bigger lift than the content selection model. So I think it's possible as well there that it's sort of a little bit of an easier problem for the seed selection bandit.
Okay. Thank you.
Yeah, but what's important to notice is also that we had one of the two experiments before the other. So we conducted the seed selection experiment before the content selection experiment. So it's possible that part of the larger lift was due to the fact that we simply ran the experiment before. And so the content selection was already benefiting from the seed selection. There were less incremental gain left on the table.
Okay.
Also, that for the content selection experiment, the candidate pool is limited by that candidate selection phase. So we're not trying to rank the whole catalog or the whole catalog of entities that match the genre, which we just can't do for scalability reasons.
Okay, I see. Thank you very much.
Okay, we have time for another question. Any questions from the audience? Okay, I have a question. So you use some context in your model. So I wonder how the context helps to improve your recommendations. Did you measure that? How does it contribute?
I can say a little bit about that, and Emmanuel might also. We've run some sort of preliminary offline experiments testing that, so we haven't run an online test. And so offline, at least, like a bandit that only uses the action features available and doesn't use the context features performs slightly worse, not a lot worse, but a little bit worse than the model with the full features. But it is significant.
So without context performs slightly worse?
Right, yeah.
Okay.
Yeah. Even in the seed selection, we've not like excluded the impact of like context only, actions only, but the control is based on like a randomized seed selection from your top genre candidates. Instead, the treatment uses a model that also has access to contextual information in addition to like richer action information to select the content. And I think also the results on the content selection portion, or like it's by comparing the T3 to the T1, the T1 does only like a popularity based, a personalized based ranking, whereas like T3 was making a ranking based on a model that was accounting for a variety of context features. And actually T3 was getting a gain compared to the control, whereas T1 was not. No, and so like it's more changes were like put together in those treatments, right? No, but like it corroborates the intuition that contextual information is important for content selection.
This is David. I would like to have a question regarding the context feature selection. Do you have any special kind of consideration? What kind of feature for the context you're going to use in your case?
So they are somewhat basic, I guess I would say at this point. So like time of day and device types are some of the main ones, but also like recent interactions. We consider as types of context.
Okay, because some of the context may have like a temporal kind of impact. Some context may valid for longer time. Some content may not. Basically, they're what called the time of their valid period may be different, sometimes dramatically different. So do you have any consideration how to use them in your model training?
So if I understand well, you're saying that different contextual information, they are more or less meaningful depending on like the window of time like you aggregated contextual information over, no? So in this experiment, what we are considering each of the contextual features we use, for example, customer affinity to like certain genre in the past, or like what a customer has done in terms of follows and how that maps to genre and so on. No? We aggregate them over different windows of times, no? Like very small windows and longer window, no? And then we trust the model to learn to make sense of the different windows.
Okay, thank you.
Okay, thank you. Let's thank first presenters. We are going to the second presentation. Maria, can you share your screen? Okay, so the second...
A moment, please, because my computer reset right now.
So you need to reset your computer?
My computer reset itself.
So are you going to present?
A moment, please.
Okay.
Okay.
Yeah, we can see you. So are you able to share your screen?
I'm going to share the screen.
Okay, so our second presentation is the paper which is called the Dynamic Inference of User Context through Social Tag Embedding for Music Recommendation. And our presenter is Mariana Garcia. Maria,
Okay.
you have 15 minutes and 5 minutes for discussion.
Okay,
Please.
thank you very much. I want to mention that this work has been carried out by members of the Data Mining Research Group of the University of Salamanca. Let's start by introducing the work. Our motivation comes from the particularities of the music domain. This is a domain where the context has an important influence on music preferences. There are several types of context that can influence the choice of the music to play by users. For example, the time of the day, the location, the activity that users are doing when listening to music are a factor related to physical context that have a great importance. But there are also other factors regarding social context, interaction media, modal context, and so on, that are also important. This factor can also be classified into environment-related context and user-related context. Many factors belonging to these categories come into play in the user session. For example, when listening to music from a streaming platform. Some of these factors are very difficult to detect and to collect. And in addition to these difficulties, considering all factors individually in the recommendation method can lead to sparsity problems, especially when prefiltering, when contextual prefiltering is performed. Another drawback is the decrease in the model performance as the number of factors increases. Aiming at avoiding this problem, we have proposed an approach to infer user context from user listening session. Our objective is to capture multiple contextual dimensions, as for example, mood, emotion, time, and so on, in order to make context-aware recommendations. Regarding our proposal, our idea is to take advantage of the social tasks that users assign to items. Social tagging, as opposed to classical taxonomies, provides a risk description of the items and has the property of characterizing items in multiple dimensions. This classification based on taxonomies has also the advantage of being dynamic and not pre-established. However, this classification has the drawback that can cause noise due to the absence of vocabulary restriction when tagging the items. In the music domain, tags can represent the characteristic of the music as well as the context indicate for a given music, for example, for a given song or a given artist. So tags are related with contextual factors. Here we can see some examples of tags from a music data set. We can see that there are tags indicating, for example, the music that is good for a given activity. such as dance, running, driving, and so on. But there are other tags that can be associated with other contextual dimensions. For example, good music, men at work, can be associated to a place, or for example, happy, sad can be associated to mood. We propose to processing tags by means of word embedding techniques in order to overcome noisy problems. Noise can be reduced since these techniques consider the context, as we can see in this example. For a window size of 5 elements, we can see that target tags such as dance or summer are surrounded by other tags that are also considered in the process. The embedding process takes outputs the vector of tags, and the output are the tags embedding vector. These tag embedding vector are used to post-filtering the recommendation in each user session. Tag embedding requires a vocabulary and sentences as input. The vocabulary is formed by all the tags in the datasets, and the sentences are formed by the tags that user give to each item. Once the tag embedding vectors are obtained, we apply PCA techniques in order to reduce the dimensionality and to simplify the process. Then each item is assigned the average PCA of its social tags. Here we can see the representation of the proposal. The first step is the identification of the user sessions. Then the training and test sets are formed by splitting the subset of songs of each section. After training and testing, we get the collaborative filtering model in charge of making recommendations. The branch on the right is in charge of representing the tag embedding process and in charge of computation the average PCA of the items. The outputs of both branches are used in the post-filtering process. First, a list of a given size is selected from the recommendations. This list contains the items with the highest predicted rating. The resulting list is ranked according to the distance of the PCA value of the first song in the user session that represents the current context, and the PCA of the rest of the item in the recommendation list. The closest the item, the higher in the recommendation list. In that way, the system can provide context-aware recommendation to the active user. In order to validate our proposal, we have conducted an experimental study with a public dataset. We use the last.fn dataset to build in the user session, since it contains timestamp data that is necessary. The tags were collected from a Kaggle dataset containing last.fn and MusicBrain tags. In this table, we can see some examples of tags. We can see that there are tags in black that are representative of the type of music, of the music features, but there are other tags in red in that case that are representative of the context, for example, quiet, at work, funny, and so on. Here we have the representation of the tag embedding vectors in the two-dimensional space after applying PCA. We can see in the figure on the right that is an amplification of a region of the figure in the left, that the tags in that region are representative of the similar music. The validation was performed by applying 4 well-known collaborative filtering methods. They were first applied without post-filtering in order to prove that our post-filtering approach gives better results. But the objective was also to ensure that tag embedding enclose the context in addition to the music features. So we implemented 2 other post-filtering strategies. One of them where the item similarity was computed from ratings, and other where item similarity was computed by TF-IDF of the tags of the items. The results of these approaches were compared where our post-filtering proposed, where item similarity is based on tag embedding and PCA. Here we have the result. The metrics applied for evaluating the recommendation list were mean average precision and NDCG. The experiments were performed without post-filtering, with post-filtering based on rating similarity, with post-filtering based on TF-IDF similarity, and our approach where post-filtering is based on tag embedding and PCA. As we can see in the graph, our proposal provided the best results for all collaborative filtering methods, as we can see in the 4 graphs, and also for all the values of N of the top N list. As conclusion, we can say that we have proposed a method for dynamic inference of user context that take advantage of social tags. The process consists of applying word embedding techniques to the tags in order to reduce the noise and to provide tagging vector that enclose the context. We use PCA dimensionality reduction technique to simplify the process. And the contextual post-filtering was based on the PCA distance between the first item of the session and the rest of the items in the top N list. And finally, we can conclude that a significant improvement of the performance of the models was achieved with our proposal. And that's all. Thank you very much for your attention.
Thank you, Maria. Thank you for being right on time. So we have time for questions. Do you have any questions for the audience? Okay, so questions. So contextual of tags representing context, so we can like better understand what's. Maria?
Sorry, I can hear, sorry.
Okay, I will repeat. So I'm wondering if you can give us.
I can hear. I
Can you hear me now?
yes, now.
Okay.
I can hear now.
So my question is if you can show us some examples of tags referring to context.
Okay. You can see my. Okay.
We see your presentation.
Yes, but I don't see it now. Okay. One moment. We can see my presentation.
Yes, we see your
Okay.
presentation.
For example, here are many tags that represent the context. For example, dance, while running, riding, that represents activity, other that represent the place, the mood, and so on.
Okay, so maybe I missed that, but can you explain how you identify if the tag relates to context, or it might be some other tag?
Well, there is no one specific or explicit context, but we assume that the tags embedding enclose are latent context. We can say a latent context with the tags, because each tag has associated embedding vector. We can see in the representation into dimensions. These are the tags depending on the context, the type of music, and so on. They are in a place or in another place or of the space. So this is the notion we want to capture. So we assume that the tag embedding vector encloses the type of music, but also the context, the latent context.
I see. So you do not explicitly differentiate between the like regular tags and tags reflecting context.
No, because when user is playing music, we take a song in the session and we compare the PCA of that song and look for other items close regarding the value of PCA close to that song in the session.
Oh, I see.
We suppose that is the context. The song in the session is representative of the context in that moment, in that session, and we look for tags with similar PCA because we assume that these tags or these songs are indicated for that context, but always is the latent context.
Okay, so if I'm getting it right, you consider two songs to which the user listens consequently, and then analyze the tags of those songs and search for those tags that have similar PCA.
Yes, that's right.
Ah, okay, and that's how you say like context should be somewhere there. Okay, okay, thank you. Are there any other questions? Okay, then let's thank the speaker. Thank you for your presentation.
Thank you very much.
So now we have a break for 15 minutes, and after the break, we will continue with presentations of papers. In the conference time, it would be at 5:05. In New York time, it would be 11:05. You should recalculate to your local time. So see you back in actually 12 minutes.
So hello everyone and welcome back after the break. So we are starting the second session of the paper's presentation. The first presentation would be exploring heterogeneous metadata for video recommendation with two-tower model by Jialing Wang. So thank you, Jialing, for joining us, and good luck.
Thanks. Hi, everyone. This is Jialing, and I'm currently a final year PhD candidate from Texas A&M University. This work was done while I was interning in Amazon Prime Video. So at the beginning, I would like to say thanks to Ali and Ainu for their help and support on this work. So our work is focusing on exploring the heterogeneous metadata for video recommendation with two-tower model. Well, in Amazon Prime Video, the video recommendation is the strong power for providing the personalization. In this task, our goal is trying to provide a recommendation on different types of videos, including movies, TVs, and even some live streaming shows. So all this functionality can be achieved by the accurate prediction for the relevant scores for user video pairs. And with such prediction, we will be able to provide a personalized experience among or across different carousels. One of the main scenarios will be we will be able to generate the top personalized list of videos and show you as movies we think you will like. And in order to achieve this goal, in our earlier work to provide these context-aware video recommendation, we adopt such a deep neural style of models. And in this model, the x-axis will include the embeddings for some user-level features, which might be some information from the user profiles. And also, we have some context information. For example, we will embed the watching history of the users, and those information will be fed from the input layer and then going through several hidden layers. And in the output layer, we will have the predictive preference scores for a whole set of items. And the size of the output layer actually is the size of the items that we can generate preference scores for. So with such a design, because the dimension of the y-axis is predefined, so if there is some new items which we never seen in the training data, these deep neural style of models will not be able to predict the preference scores for those items. And this is the main shortcoming for these deep neural models. In order to improve the flexibility, we are trying to transfer to these two-tower style of models for supporting the video recommendation. As a brief introduction, these widely used two-tower models usually has two major components. One is the user tower, which trying to generate the efficient user embedding. And there is also a separate item tower, which will have the user input and also the user encoder to generate the item embedding. And with the with the informative user and item embedding, we'll be able to generate the their preference scores based on their the dot product operation. And this is the two-tower model, and it is really flexible and also has been applied on different types of applications. So on why we say that these two-tower model are pretty flexible and also like a strong candidate for our context-aware video recommendation. So if we look into deep into these models, on the user tower, actually we can still keep our original structure for the user input embedding. So here on the user tower, we can still keep the user level features, and also we can still have the watch history embedding, which is the context information. And in the user encoder, we will concatenate these two types of information, and then we can also have some residual blocks to enable the deeper embedding for such a representation learning. So with such a style, the context information of the user can still be retained in this model and can be helped to support the recommendation for the video. So with such a two-tower model, what we still need to figure out is how we can design a good input for the item tower, and also how we can figuring out the efficient item encoder so that we can generate the informative item embedding. And our whole project is focusing on these, trying to deal with these two challenges. So the first part is the design for the input of the item tower. So we can mimic the situation while people making decision for watching a video they haven't met before. So if we are landing on the title page for the video, usually we will look into the synopsis, the categorical information, and also the cover art while we want to deciding whether to watch this video or not. So in this system, we can also mimic this process and adopt those metadata that's showing on the title page to and use them as the appendix information to characterize the items for this video recommendation. So the first types of metadata that we use is the categorical features. And in this project, we include different types of categorical features, which covers the genres of the movies and also the actors and director list. And we also have some other categorical features like the maturity ratings, the countries of origin. And we also introduce two categorical features to indicate the popularity and the time for the specific videos. And another type of important metadata is the synopsis. So if we look into those textual information for the movie, we know that sometimes some words in the synopsis are more informative. For example, in this the Twilight synopsis, some of the keywords here can hint on the genres and the topics for the movies. So we are trying to figuring out a better way that we can generate the representation for the synopsis while highlighting those important words. So in order to achieve this goal, we use this pre-trained word-to-vec embedding to represent each of the words in the synopsis. And then we also introduce the TF-IDF to indicate the importance of the words. And we are using these two components to generate the weighted representation for to represent each of the synopsis. The third type of metadata that we are using is the cover art. In order to generate the embedding for to represent the cover art information, we follow some works in the computer vision areas, and we use the pre-trained ResNet. We take out the last layer of ResNet to generate the cover art embedding. So now we have the input that includes the synopsis embedding, the cover art embedding, and also the categorical embedding. In order to better memorizing the items here, we also have the item ID embedding. So note that this ID embedding, if we are coming across some cold start videos that we don't know is ID in the training phrases, for those code items in their inference phrases, their ID embedding will set to be all zeros. And these are the order information that we can use as the input for the item tower. So what about the item encoder? We know that all these information for the items are coming from different modalities. So in order to fill these different types of metadata in a more efficient way, here we adopt the idea from attention layer. And this attention layer will be able to generate the attention weight based on the importance of different embeddings. And this weight will be first multiplied to different embeddings. And then the weighted embedding will be concatenated together before they are generating their final item representation. And with such a design of the attention layer, the more important information from the information from the more important modality will get higher attention score, and so that they will be focused a lot while generating their efficient item embedding. And this is the whole structure for our two tower models for the video recommendation. So our next step is trying to conduct some experiments to evaluate the effectiveness of such a two tower design. So due to the confidential issue, we are not able to tell you what's the exact day that we conduct our experiment. But here is the a simple setup for our experiment. So here the training data we are formulated as a supervised learning problem. So in the training process, we will use the data that's spanning for 2 years, and then trying to use the labels in the next 2 weeks. And the training data and the training process will be based on these 2 years and 2 weeks data. And then in the testing phrases is similar. And we are using the first 2 years data to infer the prediction, or we say the recommendation for the next 1 week. And the data is super sparse compared to some public data sets. So this is also another challenges while we are dealing with these video recommendation task. And to evaluate their performance, we adopt the top K evaluation here. The K is set to be 6 because it's the we want to follow the recommendation scenario on the Amazon homepage. So we use recall and precision, which are two really popular evaluation metrics that we can use to evaluate the how the top K performance are. And because we also want to evaluate how the coverage rate of these, how we can how much different items that we can recommend to the users. So we also introduced the coverage and the converted coverage at K to evaluate its performance. For example, the converted coverage at K is used to represent the number of unique items recommended to all of the customers in their evaluation set among top K. And those items should be actually watched by the users. In order, for the parameter selections, here we select the negative sampling rate to be 20, which means that for each of the positive samples here, we will randomly select 20 negative samples to chain together with those with these positive samples. And the residual blocks is 3 that we select for the user tower. And we use Adam to optimize the training process of these two tower model. And the embedding size before the dot product is set to be 512. And these are all our preparation and the setup for our experiments. So in the results part, the first figure here we are sharing is the performance on the warm start video recommendation. So here, the NCF extension is the extension version of NCF because for the fairness comparison with our model. And if we look into our version, our model that without the so even without the ID embedding, that means we only use the synopsis, the cover art, and the categorical features. We can see that the proposed two-tower model can outperform the NCF extension, which means that those metadata and the way that we utilize them is like a good selection so that it can help it to beat the NCF extension. And the next thing that we want to examine is whether the like the attention layer that we propose here can be a good choice for like fusing those different types of metadata. So here we compare the simple concatenation with our attention mechanism, and we can see that the attention mechanism can help to improve the like the recommendation performance by a lot, which means the design of such a attention fusion layer is like good design for such a fusing like operation. And another important task for our two-tower model is we want to like enable the co-star video recommendation. So the co-star video here is those video that haven't show up in the test ground truth, but like so like it means that the item that's showing up in the text ground truth but didn't have any historic interaction in the training data. And these co-star video recommendation experiments are focusing on the recommendation for this specific set of co-start items. And if we look into the recommendation performance, we can see that for the second line here, if we use it without the ID embedding, we can see that like it can have the best like recall and precision performance. But if we use it with the ID embedding, it can have the improvement for the coverage and the converted coverage. So we can see there actually is a trade-off between the precision and the coverage while we are generating the co-star video recommendation. And at the last of the experiment, we also visualize the like the attention weight that we generate from the fusion layer. And from the figure, we can see that the weight for the cover art usually is the lowest, and the categorical features usually have the highest weight, which means that in this model, like the cover art are less important compared to the categorical features. As some brief takeaway from our like our works. So here we introduce 3 new types of metadata to characterize the videos, which is the categorical features, the synopsis, and also the cover art metadata. And we find that the proposed attention mechanism can help to achieve the best performance in fusing the features from different modalities. And in our experiment for like both the warm start and the cold start items, we find that the method with ID embedding can work the best for the warm start items in their offline experiments. And the cold start items, for the cold start items, the method with metadata only works best. So in the future, there are several other works that we can conduct to extend our current work. So one thing that we can think is whether we can learn to initialize their ID embedding for cold start items so that we can achieve fast adaptation in such a cold start recommendation. And the second work that we might try to do is trying to figuring out a more efficient way to generate the negative samples while we are doing the recommendation with such a two-tower model. And if you are interested in more details or if we have any questions, please feel free to contact us with the email. Thank you.
Thank you so much, Yeling, for a great presentation. Any kind of questions? Yes, Konstantin.
It was clapping, it was not raising hand. Thank you for your presentation.
Thanks.
I have a question about the attention mechanism that you use in the item features. So basically, you use kind of attention mechanism to find the right kind of features for the item embeddings or item features. Have you tried to do that also for the user side, for the user tower, or also fusing the user features with the item features in some kind of attention mechanism to find maybe context as much more information or importance as the item features?
Yeah, thanks for your question. So in this work, we didn't because I haven't had the chance to try that. But I think the first thing is of course, this attention layer can be applied to also in the user side and trying to figure out what's the most important features for the user. And actually, this work has been done by there's some related work that show that this can be a good choice. And also, I think, yes, we might also be able to also try to use this attention layer to combine the user features and the item features. And with the main idea of the attention layer, I think it can do a really good job in figuring out what's more important, and the important part will be highlighted so that it can help to achieve improvement for the recommendation or even some representation learning task. Yeah. Thank
you. And also another question is about the user's watch history. How did you really represent this contextual information of the user? Was it the sequences of the items, or was it embeddings or some kind of pre-processing step?
Yeah. So for the watch history here, of course, because the watch history usually is in sequential patterns. So in the works, we use the the RNN style models that we can use to generate an embedding for the sequential watch history. This is the main context information that we include in this user tower. And yeah.
Thank you. Any other questions? So Jeling, thank you so much for your presentation. And we'll move on to the next presenter if he's here. Youngjun, are you here? So I don't see the next presenter. Probably had some kind of problem to connect. So in the meantime, we'll have a break, a longer break. And again, if the next presenter will be connecting, so we'll continue.
So when are we coming back, Moshe?
I will just show it on the screen. So basically, we'll
in
come
half
back
an hour.
In half an hour, in 5:45.
Okay, great.
So see you after the break.
Six, not 5:45. Hi, Anint. Okay, can you hear me?
Yes, good morning.
Hello, nice to see you.
You too.
It's early morning in Washington.
It's not so bad now.
Okay, that's great. So I made you co-host, so you would be able to share your screen. Would you like to test?
Yes, please.
So just click share screen and...
Yes, I have so many windows open. I'm just looking for my PowerPoint slides.
Oh, okay.
If I can't do this, I'll just share the entire screen.
Yeah, we can see your screen.
Great. Okay.
Yeah, perfect. So we have another 7 minutes. Francesco will introduce you.
Great.
And ask tough questions.
Looking forward to it.
Not really. I don't think so. Finally, we were able to have you to this workshop. I mean, we tried several times.
Yes, timing was not good, but
No, I see. I'm joking, but I'm happy that you are here today.
same.
Anand, are you able to complete your talk in 40 minutes? Because we have allocated 50 minutes in total, so that to leave, let's say, 10 minutes for questions.
Yeah, that should be fine. The talk is obviously the slides. I have more slides than I could possibly fit in 40 minutes, but I'll just cut as I go through.
Okay, good. Should we start or should we wait a few more minutes? What do you think, Konstantin?
Let's wait for another minute and then start. Should we start, Francesco?
Yeah, we can start. Okay, so so welcome to this last session of the workshops on context-aware recommended systems. And it's a great pleasure, and I think it's honor for us to have here Professor Anin Day. Anin is professor and dean of the Information School at University of Washington. And for sure, Anin is very well known in our community for his early work on context and on the definition of context. And actually, I want to use, let's say, a couple of minutes to recall this definition that is in this paper, Understanding and Using Context. So Anin's definition is context is any information that can be used to characterize the situation of an entity. An entity is a person, place, or object that is considered relevant to the interaction between a user and an application, including the user and the application themselves. So it's a very wide, let's say, perspective on context. And I think that this definition has motivated a lot of research on context, especially in the area of recommended system. So today, and it will report on some of the research that he is doing in the last years, where he is focusing on collecting data from about people and how they interact with the devices in order to, let's say, understand the influence of context on their behavior and try to apply machine learning techniques in order to make predictions. So the title of Anin's talk is Using Everyday Routines as a Resource for Understanding Behaviors and Making Recommendations. So I'm really looking forward to listening to your presentation. Anin, the floor is yours. So please go ahead.
Thank you, Francesco. Thank you for the very kind introduction. It's really an honor to be here. I've known about and followed the work in the CARS workshop for many years. And I continue to follow it. In fact, I was looking at a paper by Moshe Unger just the other day, looking at some of your work, Moshe, in latent context-aware recommendation systems and seeing a really strong overlap with some of the things that we're trying to do. So I'm interested in us engaging in some of these conversations around this. So I want to tell you a little bit about the work that I've been doing, my research group has been doing for the last 5 years or so. And that is, it really stems around this idea of routines. So if we think of context as being, a description of a situation in a moment in time, we can think of routines as a collection of these moments in time strung together. So what you're seeing on the screen here is the routine of somebody who wakes up in the morning and then a student that's going to school. And you can see that this routine has members, individual contextual moments. It has a sequence implying one thing follows the other, although it doesn't have to be a strict sequence. Each of the members have a particular duration of time. And then one of the interesting things is that just because someone has a routine doesn't mean they follow that routine all the time. They may deviate from that routine. That may be, today I woke up sick, so my routine is very different, and that would be an anomalous deviation. Or it could be, I live in Seattle, it rains quite often, and on a rainy day, my routine differs slightly in that I don't wait for the school bus outside, I wait for it under my awning at my house, and then I go outside. So that would be more of a regular deviation. And knowledge of these routines and deviations can actually be quite powerful when we're thinking about building autonomous systems. There was this first day website and then a book that was created called The Daily Routines of Famous Creative People. And what the author did was he went back and looked at old manuscripts and old journals from people from the arts and the sciences, from all walks of life, and tried to come up with what was a routine day for each of those individuals. And so you can see here in the sort of light blue and green is when they slept. Their creative work is in pink, this orange color, salmon color. Exercise is in this dark navy blue. Day jobs, not many of the people on the screen had a day job. Only a handful of them had things that they did during the day that was not part of their creative work. And then you can see sleep at the end. And so what this author did was say, okay, I'm taking all of the information I know about this individual and I'm crafting this timeline of how they spent their day. And now with that information, you can start to do prediction or make recommendations to someone based on what you understand about their routines. In a similar kind of way, we should be able to do that in today's world, but without having to rely on those journals or those manuscripts to provide us this kind of information. Think about all the objects that you might interact with on a daily basis. So in order to figure out what are all the objects that you touch and what all the things that you interact with to sort of build up this routine over time, this is fundamentally a multimodal AI problem. You need to be able to sense, you need some intelligence, you need to be able to communicate. And so some of the work we've been looking at is what are those novel data science and machine learning techniques that we can use to extract routines from these large corpora of data and to be able to extract routines and deviations. This was another book project called A Day in the Life, and it was a picture book. It started as a photo exhibit and then became a book. And this took pictures of, the artist had individuals take pictures of all the objects they touched in a single day. So this one, I don't know if you can read it down at the bottom, it says, A Day in the Life of Lauren Spencer King, artist and meditation teacher from Los Angeles. And the book is called Everything We Touch. And so you can see here a lot of clothes, some food, more clothes. The interesting thing is the only computational things on this, in what this woman touched each day, was her mobile phone in the top right and her laptop here. And otherwise, everything else would have to be sensed in some other mechanism than what we traditionally think of, like some kind of instrumentation. Take another example. This is a chef from Marrakesh, and not surprising, most of his objects that he touches every day are related to food. But you can see his Mac in the bottom right and his mobile phone in the top left. And there is an electronic toothbrush or electric toothbrush up here. But for the most part, most of the things he's interacting with are analog devices that don't have sensing or computation built into them. So coming up with people's routines, much in the same way of sensing context, is a real challenge, and often we have to use proxies for those sensing. So why are routines important? Well, we develop routines to reduce our cognitive effort, right? I don't have to think about my morning routine because I've kind of offloaded it to it. I kind of can enact it without having to think a lot about it. I'm able to, I know what time I have to wake up my kids. I know what time I have to leave to go drive my son to school. All of these are sort of built in to the point where I don't have to think about it, except in the case of a deviation. When there is a deviation, whether that's a regular deviation or anomaly, that's a place where there's often stress or extra effort has to be exerted because I can't just rely on this sort of background process. And I will argue that routines are at least as actionable as sort of low-level context inferred activities. Routines have really been untapped as a resource for both from a sensing perspective and from an application perspective. They really, I think routines can provide a novel way of trying to understand human intent, which I'll argue is sort of the basis or the reason we want to have context awareness. Routines are longer term, which is kind of interesting because people develop routines over a period of time, so they're more built into our lives. They do highlight opportunities for change. If I can see that I'm tired all the time, if I look at models of how I'm sleeping over time, I can see that I identify places where I might actually be able to get more sleep. So they do provide opportunities for change. However, at the same time, they provide barriers for change because something that's built in or something that's a routine over time, it might be harder to change, in fact, are harder to change. So we are working on software to try and address all of these things. And really, the opportunity to study routines and make interventions and I'll argue that interventions are in the health domain, which is mainly where I work, interventions are really a form of recommendation system. What is the thing that you're asking someone to change or do so that they can improve some behavior about themselves? So let me get a little bit concrete and talk to you about one of the projects one of my former PhD students worked on, Matthew Lee. He's now a researcher at the Toyota Technical Institute, Toyota Research Institute, sorry. So he built a system called DwellSense, which was really looking at the activities of daily living for elderly individuals. And so these activities that we try to monitor, so to understand whether an elderly individual should be able to live independently, taking medicine, doing laundry, keeping up with news, balancing finances, making meals, communicating on the phone. These are all things that we look at to see if someone can continue to remain independent. Matt built a series of technologies, very simple technology. So here's a very cheap pillbox that he instrumented, you can see. And this pillbox can tell which day of the week you opened. It can tell whether you've turned the pillbox upside down, whether you've taken pills out. So it gives you information, some rich information about someone's interaction with the pillbox. With the telephone, he was studying how many times someone made a call before they actually made the correct call. So you may dial the first 3 digits and then hang up because you dialed it wrong. You may dial the whole number and realize you called the wrong number. So these are all signs of cognitive activity, cognitive success. And then here's an instrumented coffee maker. It's not the prettiest thing with sensors and wires hanging off of it, but he instrumented it to sort of follow the coffee making process, from adding the water to the filter to the coffee grounds to pulling out the pitcher and pouring the coffee. So with this instrumentation, you can watch how people are performing these fairly simple activities of daily living. This is an example deployment. You can see our laptop that's collecting all the information is behind this woman's TV, the pillboxes here on her table, and it's just a typical living room in one of the apartments that this was deployed in. In each apartment, in addition to the technology, we deployed a tablet that had a very simple display. It just showed you how you behaved on the previous day. So today is Saturday, and this would show the data for Friday. So here you can see that the person took their morning medicine on time, but they opened the Sunday and Monday days before they correctly opened the Tuesday slot. In the afternoon, they actually missed their afternoon medicine. And then it gives them a score on how well they did from a timeliness perspective and a correctness perspective. For phone call making, they made 8 calls, 2 of which were missed dials. And it again gives them an indication of how well they did. And then for the coffee making task, it showed that they successfully completed the task, but they repeated one of the tasks twice. So it provides a little bit of feedback, again, not real-time feedback, but feedback about the previous day about how well you completed these different tasks. So what impact does this have? So what we can see here is, and let's just focus on the top graph. You can see here that if you think of this as midnight and then down here as midnight again, each column is considered as a day. And so this is the beginning of the day, this is the end of the day. And so this collection of data up here, these dots up here, indicate the morning time when people took their morning medication. And this time here indicates when they took the evening medication. So you can see for this individual, sent through Matt's pillbox, that for the most part, they're taking medicine over a period of 2 or 3 hours each day. But for the most part, they're taking their medicine on time. There's a few days when they actually miss their medicine, and then there's several days where they actually took the medicine late. In the evening, this person did much better, where they're basically taking all their medicine on time within a very tight window, with only maybe a single mistake here where they took their pill late. This is a second patient. They only had morning medicine, and you can see that they also made several mistakes in taking their pills late and making a mistake with their pills. So these displays or this visualization that we're seeing so far was taken only with the data collected by the sensor without having the display in people's apartments. Once the displays were added to the apartments, you can see how clean the signals become. For both, in this case, the person didn't have to clean up their evening signal that much, and they still made a couple of mistakes, but you can see how much better they performed in the morning medicine. And for this individual, you're still seeing lots of cases where they took their pill late for them, but that for the most part, their signal was cleaned up quite significantly, in that this intervention, having the display about what happened the previous day, did as an intervention for how they took their medicine. So it really did improve their medication adherence for these two participants. And across the board, we saw for all of our participants an increase in adherence, a reduction in the variance, an improvement in the timeliness when they took their medicine. And we saw similar improvements if you look at the coffee maker and the phone call making tasks as well. So here's just a very simple example of how routines can be leveraged. And it turns out that if you study these routines, you'll find that there's a very strong correlation to how routine people's behaviors are and how well they perform on a cognitive test that's commonly given to elders called the mini mental state examination, to the point where studying people's routines can actually replace needing to do this evaluation, because the routines have such a strong signal on them about someone's cognitive state. So this allows you to do automated, cheap, and repeated assessments without requiring an occupational therapist or physical therapist to come in and perform these kinds of tasks. So I want to point out one more concrete example that occurred during our study that might indicate the value of routines. So here we have an individual who started in our study in August, and you can see they were doing okay. They were mostly taking their medicine correctly, and we're not seeing any mistakes other than in terms of forgetting to take their pills. But several times they started taking their pills late in the morning, and you're seeing mistakes in the evening as well. So the patient's doing well from August to November. In January, the patient had a bad fall, was hospitalized, and died in the hospital. And what we can see in November to January is lots of mistakes happening in the pill taking. Now, we were not monitoring this data in real time. And in fact, when the patient went to go see the doctor in December, and the doctor said, "How is everything going? Are you taking your medicine?" And the patient assured the doctor, "Yes, I'm doing fine. I'm taking my medicine, no problems." But we can actually see here is lots of mistakes in the medicine taking behavior. So if we were to run an anomaly detection system, you would probably see in December, an anomaly would be indicated, and an intervention could have been taken at that point in time were the data being looked at in real time. So not saying that being able to detect this and intervene would necessarily have saved this person's life, but the potential certainly is there. So like many of you, we leverage the mobile phone to do our multimodal sensing for all the obvious reasons, full of sensors. Lots of people carry them, just a very handy device to be able to use. So what can we do with such smart devices? So I gave the example of the medicine taking, and now I want to talk a little bit about another sort of simple example of being able to leverage the mobile phone to detect routines, but this time around driving. So these are, I used to work at Carnegie Mellon in Pittsburgh, Pennsylvania for many years. And these are two places in Pittsburgh. And if I were to optimize for travel time, so I wanted the shortest travel time, this is the route that I would be given. And instead, if I wanted to optimize for shortest distance, this is the route I would be given. And not surprisingly, if I change my optimization function, I get a different route. But there's lots of things we care about. We care about how much it costs. So there was a study done several years ago that said if costs of tolls doubled, 73% of the driving population would avoid taking those toll roads. So we're pretty cost sensitive. We're also sensitive in how willing we are to deal with different kinds of congestion. Some people will leave hours early to avoid congestion. You have to have routes that actually match a driver's skills. And what you understand is that there are a lot of different factors that go into determining what my driving routine is. And while I'm not going to argue that my driving routine is as unique as a fingerprint, we can kind of think of each person's routine, whatever the domain is, in this case driving, can be seen as a bit of a fingerprint. So if we think about route recommendation, everybody knows that you can use an algorithm like A-star or Dijkstra's algorithm, and you can find out the shortest path from start to goal just by traversing the network. Instead, if we look at what path somebody took, and we have features of the road network, could we instead find the behavior or routine that explains why they took a particular path? So rather than just taking the shortest path, I may take a slightly different path along the top or along the bottom. And by observing how people drive over time, are we able to understand their preferences for each different features? And those features might be the speed limit on a road. It might be the amount of congestion. It could be weather that day. It could be all sorts of things that impact the road network. And so we can take an algorithm that basically looks at what is my current state? What is an action that someone took that took me to a next state? And you can build a network of these state action pairs over time by looking at these large behavioral models or collections of data about people's routines. So just as a quick example, you can see someone's in a state, they're approaching a particular, this is very simple, they're approaching an intersection. The action is that they brake hard because somebody's in front of them. Then they enter the intersection, they start a little bit of gas, they start to exit the intersection, and then they push harder on the gas to exit the intersection. So that's a fairly simple one where someone's just sort of moving straight through an intersection. And so what can we do with this kind of routines, and where is the value for recommendation systems? Well, if we can build information that learns our preferences for driving from repeated surveying of someone's driving just from their mobile phone, well, you can start to do personalized route recommendation. So I know that I like to drive on roads that have high speed limits, but has a lot of traffic. I don't mind the stop and go, right? Versus my wife prefers to drive on roads that have slow speed limits and less traffic because she doesn't like the stop and go. So even though we might be going to the same place in separate cars, we would get routes that actually match the way we like to drive. Similarly, we could do vehicle prediction. We built a system based on understanding people's routines that can actually automatically turn someone's blinker on to indicate that they're going to take a left or right-hand turn in advance, because that's actually the not using one's blinker actually leads to a lot of accidents. So there's a bunch of different things that with knowledge of how someone performs a particular routine, in this case driving, that you could build, and there's others on the screen that I won't have the time to go into, but that are applications where recommendations could be made, whether it's an individual route, whether it's a change in route because there's a hazard coming out, whether it's a recommendation to take care of something on my task list because it knows that I'm going to be taking a particular route to go in a particular direction. Similarly, this can be applied to solving a safety issue rather than a convenience issue. So if we look at the number of people that are impacted by unsafe driving really due to aggressive driving or novice drivers, we can see a lot of fatal accidents and a large cost, financial cost of being aggressive, being what we call road rage. And so as I've said, these driving routines are unique, but can we use these driving routines now to determine aggressiveness? And it turns out with about 90% accuracy, we can determine whether an individual driver is an aggressive driver, whether the route that they're on right now is an aggressive path that they took, or whether this particular maneuver that they took in this one intersection would be considered aggressive. And so we've been working on interventions that we could show to individuals to help them at least demonstrate how they might be less aggressive. So what you're going to see here is how an aggressive driver moves through an intersection. And then overlaid on top of that, you can see how a non-aggressive driver would have done that same thing. So let me just pause that for a second. Pause that. So what you'll see first is how an aggressive driver is just sped through the intersection. And then on the second pass through, you'll see what the aggressive driver is showed in gray, and the non-aggressive driver, a simulated non-aggressive driver, is showed in white and highlight the difference. So here's the aggressive driver. And now the non-aggressive driver is shown in white to highlight the difference of how a non-aggressive driver would have driven in the same situation. Second example, someone is trying to take a left turn through an intersection. And so you can see non-aggressive driver slammed on the brake, and then they accelerate through the intersection. And a non-aggressive driver, a simulated non-aggressive driver, would have had a smooth path through the entire intersection. So these were just very simple interventions to try and convey the behaviors that aggressive drivers were exhibiting. We had to play a lot with when was the right time to show them. We did the obvious dumb thing, which was to show them their aggressive driver right after they performed an aggressive maneuver. And that just made them more aggressive. So that was clearly a bad idea. But we found that waiting too long, say at the end of a week, was too long from the actual incident to impact change. So where the sweet spot we found was to show them these recommendations or interventions at the end of the day or at the end of a drive. So, and that had more impact on them recognizing that they were driving aggressively, and actually for a short time at least, reduce their aggressiveness in their driving. Oops. I'm going to talk about one more example as I move into my last couple of examples here. This one is in the case of hospital readmissions, and here we're looking at people with using mobile phones and a wearable device, a simple Fitbit or Apple Watch that collects information about sleep and steps. And I was working with a collaborator who was very interested in studying whether we could leverage this kind of routine information for people who are recovering from surgery. So you can see here on the screen that 13 to 37%, so about 1/10 to 1/3 of surgery patients are readmitted within 30 days of discharge. And in the United States, the way that the medical reimbursement system works from the federal government, if anyone is readmitted within 30 days of being discharged from the hospital, the hospital system makes less money on those patients. So they have every reason to try and stop patients from being readmitted at all, because that's a burden to the healthcare system, but really to stop them from being readmitted within these initial 30 days after being discharged. And you can see here that readmissions cost the health system $26 billion, of which 17 billion of that was considered to be preventable, which means that if we could detect someone who is more at risk for being readmitted, then there might be interventions that we can put into place, recommendations that we can put into place while they're still in the hospital, before discharging them, to reduce the likelihood of being discharged. And so we were working with an oncology population, a cancer population. And so this was a population that was going to come in to get surgery, a scheduled surgery. Before the surgery, for a month, they wore a Fitbit, they had our instrumented smartphones, and we gave them the software and the Fitbit device a month before at their pre-operation appointment with their surgeon. Then they came in for surgery a month later, and they were in the hospital, and we collected information basically from the time they went to the recovery room after surgery all the way to discharge, and then we followed them 60 days after discharge. All the way through, we also had access to their electronic health records. So we had fairly detailed information about what was happening. And it turns out that using routines, we could predict with about 85% accuracy, so not good enough to be able to use in practice, but certainly better than many of the state-of-the-art approaches. We could predict which patients were going to be readmitted. And in here, what was really the case was how much were the patients able to move. So the Fitbit was the most valuable feature, the most valuable sensing. we were looking at how much patients were able to move, or the key feature I would say in our model was how much patients were able to move and how frequently. It wasn't that someone was able to get up and take 2,000 steps in one go, but it was how frequently were they getting up to move, because this was a sign of, or a proxy for pain. If the patient was in too much pain, they wouldn't have been able to get out of bed, and they would have these long sedentary bouts. So in fact, if you start counting up the length and duration, the duration and frequency of the sedentary bouts, that is a very strong indicator of whether someone's going to be need to be readmitted within that 30-day period. So the last set of projects that I want to talk to you about, and these are the ones that I've been spending much of my last couple of years focused on, is around student health. I have a number of collaborators who have been interested in student health, particularly as it relates to substance abuse. So in this case, we're looking at binge drinking. So I had a colleague when I was at Carnegie Mellon, he was at the University of Pittsburgh, and he's an expert in interventions, text messaging interventions for people who binge drink. So a binge drinker is not someone who is an alcoholic, someone who has an addiction to alcohol, but is usually of a particular age, an adolescent to young adult, who will binge drink to excess, mainly for social reasons and not for addiction reasons. Unfortunately, binge drinking leads to a lot of hazardous issues. There's high rates of alcohol-related problems, a number of comorbidities that result. And the interventions have not really changed how people behave in choosing to drink or not. So his typical approach would be that he would send a text message on a Friday and a Saturday night, and giving a bunch of reasons why they shouldn't go out and binge drink. And while that has some effect, it doesn't have enough of an effect to really engage with them about their binge drinking behavior. So he said, with your analysis and routines, do you think you can detect or predict when someone's going to binge drink? I'd like to be able to get them at the moment in time when they're going to binge drink, so I can have my interventions more temporally co-located with the action they're going to take, right? Intervene at the point of decision making. And so I went away, talked to my team, and we're pretty sure we could not make any impact on this problem, because how would we, we didn't really see a sign or a signal. We didn't think with our, with our smartphones or wearable devices that we'd be able to detect a decision point where someone was going to choose to binge drink. So we said, let's instead see if we can detect when somebody is binge drinking. If we can detect that moment, then maybe that there are other interventions that could be made that might be useful, not as useful as predicting in advance, but still might be something that's useful. So we collected data from 38 people, and what you can see here on each individual is a vertical bar. You can see the number of incidences of non-drinking episodes that they reported. In blue, you can see the number of incidents of drinking episodes, and then in orange, you can see the number of incidences of heavy drinking episodes. And some of our participants didn't report very many episodes. Some of them reported a lot, with very few, most of them being non-drinking episodes. But we did get a lot, you can see in the orange, we did get a fair number of drinking episodes and heavy drinking episodes or binge drinking episodes that we were able to collect. And I should define binge drinking or heavy drinking. It depends on body mass index, so it really just depends on what state your body is in. But for the average female, it is 4 or more drinks in a period of 2 hours. And for the average male, it's 5 or more drinks in a period of 2 hours. So fair number of drinks in a fairly short period of time. And you can see, if we looked at day of the week, how the drinking episodes are distributed, and you can see mostly the heavy drinking episodes are happening on a Thursday, Friday, Saturday, Sunday. So those are what we characterize as the weekend. And in terms of when they occur during the day, you can see that they sort of start around 6 p.m. and they continue to maybe around 3 o'clock in the morning. And that there's not a lot of heavy drinking or binge or drinking at all during the actual daytime. So if we built a model that was just based on day of week and time of day, we could already do quite well, but that's what the text message intervention was already doing, and it only had limited effect. So we built a model that took into account a lot of different sensing, and I'll go into a little bit of detail. I have a few minutes left. I'll go into a little bit of detail on some of the features that were relevant to building an accurate model. But you can see here that we built a model that was so this is a confusion matrix, was very accurate at detecting the non-drinking events, almost 98, a little over 98% accurate. And it was fairly accurate at detecting the binge drinking events, 91%. But where it made most of its mistakes was in detecting the light drinking episodes. So it confused those not for heavy drinking, but it confused those for not drinking episodes. And we're not still trying to understand why. When the heavy drinking, when the classifier made mistakes on heavy drinking, it misclassified those as non-drinking as well. So there's a bias towards, and not surprising in the data we see that, there's a bias towards non-drinking. But overall, you get about 95% accuracy. And if instead you just went with a time of day or day of week, or you picked the most likely class, you're looking at about an 82% accuracy. So fairly sophisticated, fairly accurate in terms of being able to detect drinking episodes, in particular heavy drinking episodes. And some of the features are going to be obvious. They were using data from the accelerometer, which was sort of tracking how people were walking across the floor. Some of them were non-obvious, like someone's use of emojis. We didn't look at the content of what people were texting or typing, but we did look at whether something was emoji or not. And we looked at frequency of mistakes that people were making. How often did the autocorrect kick in? When they were using the keyboard. And we saw that their use of emojis shifted dramatically as they went from a non-drinking state to a drinking state to a heavy drinking state. So there are signals in what people are doing that can at least help you detect in real time what state someone is in from a drinking perspective. Our newer work is actually starting to look at, can we predict binge drinking episodes in advance? And it turns out with a window of about 6 hours of data, we can predict about an hour, it's only an hour ahead of time, but we can predict 1 hour ahead of time with about 85% accuracy that a college student is going to binge drink. So this is really exciting, because then an hour ahead of time, hopefully before they've made a decision that they're going to engage in this heavy drinking behavior, interventions can now be applied, or recommendations can start to be made that would actually significantly alter someone's behavior. So right now, this work is being integrated into a 5,000 person intervention trial, a recommendation trial. And we've extended the work to start looking at, we've started collecting some data with individuals who are under the effect of marijuana, and we're starting to look at individuals who are under the effect of opioids, and looking in particular at when they might have cravings and might have a relapse for somebody who's trying to reduce their use of opioids. The very last part of this work with college students and substance abuse led to some other work that we are doing, looking at mental health in general of college students. And here in the United States, many college students feel overwhelmed, many feel exhausted. 1/3 of college students feel too depressed to function, and 1/16 of them have seriously considered suicide. And so there is a real mental health crisis amongst a college age population. It doesn't have to just be college students, although this happens to be the population we're focused on, but that age group in general, college student age group, there is a mental health crisis going on in the United States and in many developed countries. For college students, this can result in lower academic performance. It increases the likelihood that they will not complete their degree, and certainly increases the risk for suicide. And so we've been looking at, can we study things like how lonely someone is, how depressed they are, what's their quality of sleep, by looking at these routines over time. And I won't go into the details too much, but we're about 88% accurate at detecting depression, that a college student is depressed, from only a couple of weeks of data at the beginning of an academic term. And we can detect or predict depression in advance, what their depression scores will be at the end of that college term, or even at midterm time when stresses increase. So we're about 88% accurate at detecting depression, about 75% accurate at predicting it ahead of time. So these are really promising. And I'm going to skip past some of this work here, but I want to say that I've been incredibly influenced by the work that's come out of the contextual recommendation system, looking at what we call contextually filtered features, but are really a set of features. Sorry, there's a car alarm going off. Really a set of features that we were inspired by work in context-aware recommendation systems, looking at instead of looking at a single feature. So instead of just looking at location, instead of just looking at when people were physically active throughout the day, we only, and looking at their location throughout the entire day, we instead pair those together by saying, let's look at physical activity, but only when they're off campus. So by pairing a piece of context within another context, we've developed this idea that we call contextually filtered features that enables us to hone in more closely on features that have higher degrees of signal. And those have allowed us to build these much more accurate systems that we're seeing here. So I'm just going to skip past some of this in the interest of time. And you can see that by using these contextually filtered features, we can get much higher rates of recognition accuracy. So in this talk, I've described that my goal is to really understand and extract this notion of routine, because I believe routines are a better way to identify what someone's intent is than individual pieces of context. We're working on a mathematical model of what it means to be routine and trying to assess, is somebody more routine or less routine than another individual? How much entropy is there in their data, in their model that we produce for them? And trying to understand what impact, whether there's a sweet spot for an individual and how much entropy there should be in their model in order to identify what kinds of recommendations or interventions could be done. We're going to be continuing to focus on mental health and substance abuse and looking to support different kinds of interventions and recommendations. And in my ideal world, I've been thinking about, could I eventually build an interactive decision support system that would allow anybody, in this case a college student, to indicate some desired outcome. I want to maintain my physical fitness and I want to get good grades. And then but I'm in this situation where I can do either A or B. Which one would actually help me achieve my outcome? As a way of supporting individuals' decisions in making those, in deciding what to do. So to conclude, I think that there's an opportunity to really innovate by using everyday objects as a resource for design and for extracting these routines. Objects need sensing, intelligence, and communication. There are certainly challenges in determining what to sense. This is true for any kind of context awareness. There's challenges in achieving good data sets because these are often large, very noisy data sets in order to collect large data sets about routines. We are still working on challenges in developing new algorithms and for both machine learning and data science. And then we have challenges in identifying what actions to take. And really those are the recommendations: when to intervene, how to intervene, and what intervention. So these are all challenges that you're all familiar with in your work in context-aware recommendation systems. And then our goal, of course, is to produce systems that can have societal impact, which is why we're mostly focusing on applications in the health domain. So I encourage you all to think about all the objects that you interact with on a daily basis and what that may indicate to an oracle or an observer, and what your routine is for the day. And what you would do if you had access to the routine information about you. So I will end with that, and thank you for your attention. I'm happy to take any questions. I'll stop sharing.
Thank you very much. Thank you very much, Anid. And now it's time for questions. Oh, Daniel Jones now is only clapping. Alex, please go.
Yeah, thank you. Thank you for the nice talk, Anid. In your binge drinking example, you referred to sensors and some other contextual information, but you went a little bit quickly over it. And the question is, in your model, like predicting binge drinking, can you talk a little bit more about how important was contextual information and how you represented and how you modeled this contextual information for the binge drinking application? So
yes, so the sensors we used for that project were multifold. For ground truth, we initially used what's called a scram bracelet, which is a bracelet, an ankle bracelet that you put on someone's leg that can detect whether they have consumed alcohol or not. You'll often find them used by people who have been incarcerated, who have to go to jail, or on some kind of probation for alcohol use. Not surprisingly, many of our students did not want to wear that because it's quite intrusive, it's embarrassing, you can't go through security, right? So instead we relied on ground truth, but some of our subjects still wore this ground bracelet. And then all of the rest of the sensing, all the rest of the context came from people's mobile phones. So we were tracking location, we were tracking movement, we were tracking activity, we were tracking what applications they used, communications they made, through either phone calls or texts. We didn't have access to anything else. We had information about what they typed. So that was the set of information that we had access to. But the features that were the most useful were accelerometer, so how they were moving through space, location to a limited degree, because a lot of the times the binge drinking happened in their own residences. And so it's very hard to use that as a feature when, that's a place where they sleep and they study and they do all those other things. And then how they interacted, how they communicated with other people was important. And that typing behavior, the number of mistakes they made, the number of emojis that they used were also really strong indicators. This was put into a fairly simplistic algorithm. It was just a simple decision tree, a random forest. With the outcomes being one of our 3 classes, not drinking, light drinking, and heavy drinking. And you can see the results that I showed with about 90% accuracy at being able to detect these different kinds of behaviors.
Yeah, thank you.
Bamshad, please go ahead.
Yeah, thank you very much for the talk. Very interesting. So this is maybe more of a comment than question, but I'm interested in your reaction. There's been a lot of work in context-aware recommendation on the idea of context adaptation. So the idea that users may move from one context to another context. You kind of mentioned that at the beginning in terms of your description of what you call a routine. And much of that work has actually been the idea of being able to adapt to a new context. So the recommender system would have to very quickly adapt when the user changes context. Let's say if you're listening to music, you change from, let's say, exercising to, let's say, having dinner or something like that, right? To some extent, it seems like your notion of intervention or recommendation is sort of the opposite of that. So recognizing the changing context, but then trying to bring the user back to the original context rather than trying to adapt to the new context. And I was just wondering if you think that's accurate and if there is some of that work from context adaptation that might transfer over to this work that you're doing.
Yeah, that's a fascinating way to look at it. I hadn't thought about it, but as you described it, it absolutely makes complete sense. The challenge that we have, so yes, we are trying to keep someone in a particular context or routine. In the case of the driving or the health behaviors, it's to keep them in a healthier state. In other cases, it's to make the deviation from the routine much less, so that it's much less of a cognitive burden. One of the challenges, and one of the places I think we can leverage much more of the work that you refer to, the context adaptation, is that we know that people's, I guess there's 2 things. There's, if we think about the initial slide I showed, which had these, this cartoon sketch of somebody going through their morning, each one of those was essentially a new context, someone going, performing a different set of activities throughout the day. While I think of those as individual contexts and that sequence as a routine, we could be thinking about, well, how should the system change as you move between those? And that's something I haven't really thought about. The part that we have thought about is, if you think that over a longer period of time, people's routines or context changes. So my routines may change seasonally, or it may change as my kids, graduate and leave the house and go off to college. And how quickly can we detect those larger changes in routines so that we can essentially learn when the model figure out when the model needs to learn and adapt? But those are over much longer periods of time, and that's where we put a lot of our focus on. But I am very intrigued by the framing that you just gave, and I'm certainly going to look at that. Thank you.
We have another question from Christine, please.
Hi, Anand.
Hi,
Great
Christine.
to
It's
see
good
you
to
here.
see you too.
My question somehow relates to what Bamshan said before, but giving a different twist. So I was wondering, in context-aware recommender systems, we frequently look on different people, different persons, we personalize, and then, okay, it's me, but I'm in a different context. So like music, okay, I'm doing exercise. So within my space of what I like, it will adapt to the context. And I'm asking whether in the work that you are doing, it's maybe other way around sometimes, that how much of the context is person related or not. So for instance, if it's raining outside, does it really matter to know what person it is? Then I'm waiting when there's a roof above my head.
Yeah, that's an excellent question. I think with a lot of, I would say, and this is a very large generalization, but for most of the work that we've been doing, particularly in the health domain, it is very much specifics about the individual and less about the environmental context. The one exception might be driving. So while there are specifics I have about the way I drive, weather outside, particularly if it's extreme weather, like a bad snowstorm in Pittsburgh, let's say, or it makes a big difference in how people drive or their preferences, how their preferences are exhibited in the way that they drive. But I would say, to reiterate, for most of our work, and I'm trying to think if I can explain the reason why. In the readmissions work, people are in the hospital, so there's the location, the weather, none of that really matters. It's how they're behaving in the hospital. So that one makes sense. For the drinking behavior, that one's a little harder to explain, because we think of environments where the weather is really extreme as being populations where alcohol is used a lot more. So you would think that it would have an impact, but maybe because we're not studying it across these large extremes, we're only studying it in a particular city, we're not able to see the value of that, of those things. So maybe the short answer, the long answer is, if we were to do some of these studies over a much wider variety of environments, we might see a larger impact of these environmental contexts as opposed to the personalized context. But that's total speculation.
Thanks a lot.
Thanks. Good to see you.
Any other questions? Maybe I can make the last question before we go to the final discussion. Anid, what you have described, let's say, I'm trying to put this into the context of recommender system, and in particular on the let's say session-based recommenders. So these routines that you are describing are typically, let's imagine that we have seen the Spotify, how people are consuming music. No, right. So one track after the other. No, what we do in recommender system is typically make predictions about what will be the next. No? And then recommendations are actually built around this prediction. I think this is totally wrong. And I think that also the presentation by Spotify today was indicating that we have to give a better recommendation. No? So this is just the detection of the behavior. And what you have shown is that the detection of the behavior is not immediately building the recommendation. The recommendation should come on top of that in order maybe to change the behavior, to maintain a stability, or to optimize some other criteria. Do you share with me this idea? Because also this, I think it's very important for recommender system. We should stop recommending the things that people are doing or the tracks that the people are listening. We should understand what is important, what is useful, what brings value in a recommendation, even deviating then from the routine in some cases.
I love that. I love that framing. I would love to see my work even move into that direction. That's a really nice way of putting it.
Okay, thank you. Good. If there are no more questions, I think that we can close with clapping.
Yeah, thank you
for the presentation and for the talk and for the QA session. And then I pass the floor to Alex, I guess, and get us that will try to make a summary, a conclusion of this workshop work. Thank you.
Yes, thank you, Francesco. So we have like 5 minutes, so we'll be brief. So we had like 2 very interesting keynotes, 3 talks, and we started this workshop Bamshad, small correction, 2009, not 2010. But 2010, when it really sort of took off in Barcelona, when we had to bring extra chairs because there were like too many attendees, so we couldn't accommodate all of them. And then at some point we stopped doing the workshops because we felt this cars managed to become part of the mainstream. And then in Copenhagen, we realized there were still quite a few unexplored topics, interesting topics, which we want to discuss. Sort of we came back and sort of continued cars. And both this workshop and like in general, we still feel that this is the case. There are all these interesting topics ranging from how do you model latent context as opposed to explicit context, context in non-standard applications, like lots of papers deal with context for music and video recommendations. It's also very interesting how you model contextual information in other type of non-standard applications, including like Anin's example of binge drinking. I don't know how non-standard it is, but usually, obviously an unusual one. So how do you model context in broader range of applications? Context extraction and inference, another interesting problem. Context for short-term versus long-term modeling. This was Luca's first industrial keynote address, obviously, an interesting topic to explore. Routines and context-aware recommendations in light of Anin's talk and subsequent Francesco's comment, really trying to understand these long-range behaviors and only then sort of providing recommendations. So there's still quite a few interesting topics to study. We still have a lot of juice in this area, and we do have momentum. The only thing which is sort of a bit of concern to me, somehow the number of attendees at this workshop was like significantly lower than at the last one, which we had last year. Probably one of the reasons is that there are like quite a few other workshops which go in parallel now, but we need to try to understand this context, pardon my pun, but you know, so like what is sort of going on, why we have this like unusually low attendance this year. Should we be worried, or this is just a matter of fact that simply too many other workshops going in parallel? We're like almost out of time, but I would like sort of to open the floor for some kind of additional last minute sort of discussions, remarks, or any comments.
I just wanted to very, very quickly add, I put a link in the chat. I mean, right, you know, a couple of days before this workshop, you know, something, you know, I have some alerts about where, you know, some interesting research pops up somewhere on the internet. Like this just popped up, like Google seems to be like redoubling their efforts on incorporating more and more and more contextual information into the search. Some of it, so you can read the article, but like it looks like the context is ever increasingly more and more important, you know, and we saw already today a lot of industry-oriented applications of that, and obviously, you know, Google is yet another example of this. So I thought that article was quite interesting, so that's why I wanted to mention that.
Any other sort of comments, remarks, suggestions?
My suggestion is that we really should try in the future to join different cultures, because this context has started. Now, when we started this workshop, we said context has different meanings in different disciplines, different cultures. We should keep, let's say, exploring these differences. And I think the talk of Anit today, which is not really, you know, central in recommended system research brought some new ideas and some challenges. I think that we should really go in that direction even in the future, trying to bring here in this community people that are dealing with context, but not in, let's say, an orthodox way in terms of recommended systems, because this can bring value.
Yeah, fresh set of ideas and perspectives. I fully agree, Francesco. Yes, Wen, you have a question? No questions. All right, well, if there are no more questions, we're also out of time. So we'd like to thank all the participants, all the presenters, I mean, Lucas, and all the speakers. And, you know, hopefully we'll do another one next year. All right, thanks again. And
thank you to everybody.
And
thank
also
you,
I'd like to
everybody.
thank particular
See you
thanks to
soon.
Moshe and Konstantin. They put a lot of work, and to all the organizers, but particularly I would like to point out Moshe and Konstantin. They put a lot of work in making this workshop a reality. Thank you, guys.
Yes, thank you.
Thank you.
Very much.
Thank you for coming.
And